In this masterclass, I'm not just going to explain how to type in a PySpark code to get the output from it. We are going from the scratch, from the core basics, all the way to how Spark actually processes this data behind the scenes. All these concepts are exactly what a real enterprise-grade data engineer has to know. And also, all the resources that I'm going to use in this masterclass, the files, the codes, everything that I use will be given to you from the GitHub link down below in the description. Without further ado, let's begin. Before we step into the first topic, I'm going to tell you how I structured this masterclass. I structured this with multiple phases, and each phase has multiple topics compressed in it. And for every topic, I'm going to explain the concept first and show you the conceptual diagram if there is any for that topic, and also I'll demonstrate the lab if there is any. That's how this masterclass goes, so you get the practical experience. I would highly recommend you to work alongside me so you get some practical hands-on experience. Let's get to the first topic. What is Apache Spark? Apache Spark is a distributed data processing engine designed to process large-scale data sets across multiple machines that run in parallel, which means unlike the other tools that we use to process the data like Python or SQL, instead of running on one single machine, we use PySpark or Apache Spark to run the same process across multiple machines, which means our data set will be split into multiple sub data sets basically, and each of those data set or subset will be given to one individual machine to run, and later on they will be combined together to get the result. This allows that particular system with multiple machines to produce the output faster, relatively faster than the system that only has one machine working on it. That is how Apache Spark works. And one more thing is, Apache Spark also offers a high-level programming model. It basically means low-level programming model, you have to customize everything by yourself manually, whereas high-level programming model is a lot easier than low-level programming model, where you don't need to deal with everything. You just write a simple code, and the compute will do the rest for you. For instance, like I said, this is a distributed machine, right? So for a distributed machine, you might think to run a task or run a job, you might just need to manually distribute those tasks by yourself with a code. But in this case, you don't have to. Spark will do that automatically for you. You don't need to distribute the data among the multiple machines by yourself. It is done by Spark, and that is why it says high level programming model, which is so simple for anyone to write. Well, the main problem that Apache Spark fixes is the scalability, the large data sets, basically big data processing. Before even Spark exists, there are multiple languages where we can distribute this process among multiple machines. But apart from that, apart from distributing the work across the machines, Spark is also known for its high level programmable model because it is so simple than the other machines to code, and that is one of the other problems that PySpark solves. There are a few other ways that you can use to distribute this task, which includes MapReduce. We will talk about it later, where you have to manually distribute the data and you have to customize everything manually. Nothing is done automatically. That is what PySpark solves. You might think, what's the reason for us to horizontally scale? Why can't we just upgrade RAM or CPU or storage on one single machine to its peak? But there is a limit where you reach the peak and you can't upgrade it anymore, and still the data rises every single day. Then what you do? You cannot. That's the bottleneck. Instead of upgrading one single machine, you can add multiple machines together to work on the same data set at the same time parallelly and get the output. And that's the major difference between vertically scaling and horizontal scaling. And also, whereas on the other hand, we have databases. Databases are good to query the data from the already stored data, but they are not good to process large scale data sets. Unless we use a modern tool like Snowflake, we cannot do that. And one more thing we have to know, we just talking about Apache Spark, but what is PySpark? Well, Spark usually is written in Scala, deals with Java Virtual Machines, JVMs, whereas PySpark allows us a Python environment. It's basically PySpark is basically a Python API for Spark, to run Spark jobs. Instead of writing the code in Scala, we can just write it in PySpark so that we stays inside the Python environment, and that will be later converted into or talks to Spark JVMs. Now let's see a conceptual diagram that I just created to demonstrate the first topic, which is 0.1. I just created this conceptual diagram to show how the architecture, the basic foundation of Apache Spark works. So it has a driver and multiple executors. Apache Spark basically works on master and slave architecture. The master controls the slaves. Okay, here the master is nothing but the driver. Driver does not execute the task. What driver does is driver creates a plan or architects the plan and makes the executor work on the task. So it splits the task among the executors. Like it says, the driver, which is a master, splits the tasks across all the executors that we have or that system has. Here I've shown 4 executors, and this will be the tasks will be split across all the executors, and the data set, one single data set, will also be split among the executors. If there are just 2 executors and 4 tasks, these tasks, 2 tasks will be assigned to one executor and the other 2 will be assigned to the other executor, and one task will be executed and the other task will wait for this task to be executed, and then this goes inside, and that's how it works. And later on, these data will be combined together to get the output. That's how the basic foundational architecture works. Don't get this as a final architecture. This just for the basic one. This is a very fundamental architecture. We will know about the exact architecture in the later slides. I will tell you which of that architecture is the exact replication. Now with that, I think we're done with the first topic. Let's head to the next one. Now talking about our next topic, which is 0.2, batch processing versus distributed batch processing. Here we're going to talk about what regular batch processing and what distributed batch processing does, and when to use what. You might think, well, like I said, PySpark is going to be faster than single node processing like Python. And think, well, I can just replace Python with PySpark in all the situations then, right? No, it doesn't work like that. PySpark comes with the trade-offs. There are situations where a single node is just fine and fits perfect, and there are a few other situations where multi-node is needed, is required, and it comes with a few trade-offs, and we are going to talk about those trade-offs now. Let's say you want a variable or an array, or let's say any object, to be global across the whole data set. Okay? To be clear, I'm going to draw something. Let's say you define a variable and say a equals 3, okay, in your data processing step. And you want to multiply a equals 3. You want to multiply a to every single row in that data set, okay? You have a data set. Right? So you want to multiply this a equals 3 to every row, column in that particular data set. When you running this processing, data processing on a single node, it is easier to execute this because everything is executed in one node, one single machine. So you can just write the logic saying multiply a equals or multiply a to every field in this particular column, and the compute will do that. Whereas on the other hand, what happens in Spark is splits this data set to multiple machines. Yes, so this part of rows will be on a separate machine, and this part of rows will be on a separate machine. When you define the variable a equals 3, maybe this machine has that variable, but this machine doesn't. So it can multiply a equals to 3 with the data in this machine. That's fine. But to multiply a to the data in this machine, Spark needs to execute shuffle, where it shuffles the data between the partitions, and that includes multiple other steps to be followed, and that makes the system slower. Well, it does the job by the end, but it makes the system even slower because it has to redistribute the data across the systems to make sure this variable is also accessible in this machine as well. And that is why you have to be careful when to use PySpark and when not to. So if you have a data that is just fine and can be executed in one single machine, just go for Python. If that data increases eventually, you can upgrade your parts or components for that single machine, and only if you get to that bottleneck where you think this is not enough, this system cannot process this data, this big of a data anymore, that is the time when you have to use Spark to distribute the data or process or tasks between across multiple systems. Or else you will end up even making the data processing slower in these type of situations where the machines need to shuffle the data between them. So we have to be careful when to pick what. I just explained one situation, which is global variable. There are multiple other situations where you need to have all the data uh, together at one particular machine to actually get the output from it. In order to do that, we have to run the shuffles. The Spark has to run the shuffles multiple times. That'll make it even slower than running that exact process on a single machine. So we have to be so careful picking PySpark and picking a single node. Now our third topic is MapReduce versus Apache Spark. Remember when I said there are multiple other tools where we can do distributed data processing, and MapReduce, Hadoop MapReduce is one of them. But they both, comparing MapReduce with Apache Spark, they both have their downsides and upsides. Talking about MapReduce, this is a low-level programming model. This MapReduce offers a low-level programming model, whereas Spark offers a high-level programming model, which we already talked about. Spark is easier and simpler to code, whereas MapReduce is quite complex. And also, MapReduce saves the data to the disk intermediately for every other execution. It has multiple stages like map, shuffle, reduce, and between these stages, MapReduce will store the data, the intermediate metadata, into the disk. Whereas Apache Spark doesn't follow that, doesn't store everything in the disk, because the MapReduce stores everything into the disk, the intermediate data. This tool is disk heavy. It stores a lot of intermediate data, whereas Apache Spark doesn't store any intermediate data, but what it does instead is it uses memory. It memorizes this data, which reduces the disk usage. And also, because MapReduce is a low-level programming model, it needs explicit key-based aggregation, and that is not automated by the tool itself. Whereas in Spark, we don't have to do that. We don't have to explicitly or manually aggregate that data. It is done by Spark. This is a visual representation of what I just said. MapReduce is so disk heavy, which uses disk a lot. If you take a look at this diagram, it uses disk at every intermediate to store every intermediate data between these steps, these stages. Disk, map, disk, shuffle, disk, reduce, disk. So it stores this intermediate data at that point of time. Whereas in Spark, disk to memory, so it memorizes that, and then transform at the end to disk. So it uses memory, and this prevents us to go back and forth. So this is not disk heavy. Spark is not disk heavy. That is what this visual representation is saying. Now we're done with the topic 3. Let's head to the next phase. Till now we talked about the foundation, but from now the real concepts begin. In this phase, our first topic will be Spark architecture. We're going to talk about all the components that are present in the Spark architecture, and there are multiple components, and we are also going to talk about what each component is responsible for. Talking about the components that are included in the Spark architecture includes a driver, like we talked before, a driver, multiple executors, and a cluster manager. And they all have their unique roles and their participation to, the process the data. Here it is. You know what? Because the topics from now on are important, I'm going to refer the document so I don't forget any topics to explain. All these components that I just listed are combined together to get these outputs: coordination, deciding what work to run, and parallel execution, working parallelly at the same time, parallel execution, and also resource management. And talking about resource management, that is particularly referring to cluster manager, and then failure handling as well. So combining all these components together gets these properties, offers these properties to us. And talking about one component at a time, and that particular component's job to do is this, starting with the driver. The driver parses the Spark code. When you write a Spark code, driver is responsible to parse the code. You know what parsing is, right? When we write any sort of code, the computation or the compute parses the code first, and which means basically understanding the code. So driver is responsible for parsing the code, building the logical plan. The flow in Spark is unique than the other any other computational, tools, where in Spark, when we write a code that is considered as a logical plan, then Spark convert this logical plan into a physical plan using something called Catalyst Optimizer, which optimizes the logical plan and creates a physical plan. And physical plan will not exactly look like logical plan. And yeah, we're going to deep dive into this topic later, but for now, just understand this. So there are multiple flows, and converting logical plan to physical plan is the first step in the flow. And that is what we are talking here. It builds the logical plan, nothing but the program that we wrote, by parsing the Spark code, and then create the physical execution plan as well in the driver itself using Catalyst Optimizer like I talked. Splits the work into tasks, schedules the tasks on executors, and tracks execution and failures. So it monitors everything uh, that is happening in the executors on the tasks. That is what driver is responsible of. Like I said, the Spark works in a master and slave architecture. So here the master is driver. So it makes sure everything goes fine, and it assigns the work to the executors, which a master does. And now heading to executors. Executors are the slaves, the workers. Executors execute tasks assigned by the driver. Driver assigns the task to executor, and executor executes them. And process data partitions. Like I said, the data is also partitioned. When the task is given, the data is partitioned across all the workers, right? And process the data partition, the partition of data that is given to that. Stores intermediate results in memory or disk. Intermediate results will be stored in the memory in that executor, and then report the task status back to the driver. Reports the task status back to the driver, so the driver knows what's going on, and driver can know there is no failed tasks in that particular job. And then there is cluster manager. Cluster manager's main job is to manage the resources or to provide the resources to the driver. So that is what it says. Allocating CPU and memory to Spark, launching executors. It also launches executors and monitors node availability. It also monitors what workers are available and what workers are inactive. So that is the job of cluster manager. They all have their unique jobs and roles in this flow, and not if the executor fails, that is fine. The work will be executed, the work will be distributed to the other executors, but the cluster manager fails, that needs to be fixed faster. And also the driver. They are more important than executors because there are multiple executors. If one fails, the other gets the load, or the other executor shares that load as well. That's fine. Knowing about these core concepts is so important before we step into the actual coding, because like I said, this should be a practical way to learn PySpark, not just type in the code and get the output from Spark. That doesn't make sense. Spark is nothing about knowing nothing. Spark is unique because of its structure and how it works, and the architecture is the main part of that. And that is why I started from foundations. Now we know the architecture. Now we head to the conceptual diagram of the architecture. And the key points here says driver is the controller, executors are the computation, just the computation. It doesn't control anything. It just executes what is assigned to that particular executor. And the cluster manager is the one manages resources. Those are the key points you have to remember. And this is the conceptual diagram of how the architecture actually looks like, the visualization. The driver, obviously on the top because the driver is the master here. It parses the program and allocates the tasks among the executors. It asks cluster manager to allocate those available executors so driver can distribute the tasks, and the cluster manager shows these executors are available, and the cluster manager launch these executors, and driver splits the tasks to them like that. So the driver first, it asks the cluster manager, and cluster manager launches the executors. After the cluster manager launches the executor, the driver then assigns the tasks among all the executors, and that's how the architecture works. I think I also have the execution flow here. Yeah, the execution flow. User submits a Spark application. We write the Spark code and submit that to Spark, and driver starts first because it needs to parse the code first. So the driver starts. Driver requests resources from cluster manager. After parsing, it requests the resources, the executors and stuff from the cluster manager, and the cluster manager launches the executor, and driver sends task to the executor after cluster manager launches them. Executors process the partitions and returns the results back to the driver. So the driver prints the results then. So the driver has all the results. The only task the executor does is to run whatever the task is assigned to that. Then driver tracks completion and failures. We talked about it already. And that is the whole picture of how Spark architecture works. With that, we're done with this topic. Now let's head to the next topic. And now our next topic is 1.2, jobs, stages, and tasks. Basically, executional units. Until now, we are familiar with the Spark's architecture. Now we are going to talk about the executional architecture of Spark, which are these three units. The relation between these three goes like a pyramid, okay? There are multiple tasks at the bottom, and a group of tasks will be called as a stage basically, and group of stages will be called as jobs. Now, when you execute an action in part of your code, part of your application, the PySpark application, when you trigger an action, this action creates multiple jobs, and one job can have multiple stages, and one stage can have multiple tasks. That's what it says here. Job is triggered by an action, stage is a group of tasks, and task is the smallest unit of execution. It's like a smallest job. There's nothing beyond tasks. Task is the smallest execution in the whole cycle. And firstly, we have to talk about the execution triggers. Like I said, an action triggers the execution and creates a job. What that means is not every line of expression triggers a job in PySpark. So if you create a data frame, that does not trigger a job. That is not an action. That does not trigger a job. But that does not create a job, to be particular. There are few functions that actually triggers execution. And a few of the common ones includes count of, getting the count of rows in one particular data frame, collect of, show of, it just shows a sample of data, and write of, it writes the data into it. So these are the common actions. There are a lot other. These type of functions are called as actions. An action triggers execution. And there is one more topic, one more concept I have to talk about, which is lazy execution. It is not included in the material, by the way. If you get the material, you don't expect that topic here. Wait a minute. I think we do have lazy execution. Yeah, there is a separate topic for lazy execution, but I'm going to give you a brief about it. Lazy execution in PySpark is nothing but PySpark only creates jobs only when certain functions are called and not for everything. If you create a data frame, or if you filter something out, or if you create a column, that will not create a job with that expression. Only when you run an action like one of these things, that is the only time when Spark triggers an execution and creates the jobs, which includes converting the logical plan into physical plan and so on. We will talk about that. We will deep dive into that later, but now this is the basic plan. And these are the common actions that are used. And talking about stages, like I said, are a set of tasks that can execute without shuffling the data across the network. There are a few situations where we have to shuffle the data across the partitions. And we already talked about it when we talked about the global variable, remember? And these are the few common situations where the shuffle happens: group by, join, distinct. And also, when you trigger this action, count off, this will also trigger a shuffle. And yes, these things are triggers a shuffle. Shuffle is basically about a situation where the data, the separated data in those particular partitions is not enough to run an action, and a shuffle needs to be happen. So the data that belongs to one particular thing has to be joined or has to be assembled in one single executor to actually perform that particular task or job. And to do that, the shuffle is executed. Shuffle boundary is implemented, where these data that is already partitioned will be repartitioned again with inputs and outputs between these executors, and all the data that is related will be assembled at one executor, and the other executors will have the rest of the data. If you didn't get that concept, I'm going to explain it with just one simple visualization. Let me just create a new slide here so I can draw something here. Let's say we are processing the data, and our data processing have one of those functions like groupBy or join, and we have the data separated among the partitions, right? And this will be the data set. This will be the data set, and data is partitioned among all the executors. Say 0, 1, 2, 3 executors. And to perform a group by or to perform a join, what we have to do? We have to group the rows that are identified by that particular group by variable, right? Like, let's say we want to group by a particular column. If there are multiple columns, we want to group by with a particular column, yes? And that particular column has the values spreaded or splitted across all the partitions. Some of the data is in this partition, some of the data is here, some of the data here. So what Spark does is, Spark first groups in this partition first separately without any communication with the other partition. First it groups among independent executors. So it groups here, it groups here separately, and what it does is it shuffles the data. So all the related data that has to be grouped comes to one single executor, and then there will be a global group by function basically, and it groups the data again globally throughout all the inputs that are given by these separate partitions together to group that again. So that is how shuffles work. So if the data is spread across partition, it does inputs and outputs between the partitions to get that similar or related data to one executor, and then executes that. That is how this works. I hope you got it. I'm going to delete this. Head back. That's how it works. And there are two types of stages. One is shuffle map stage and the other one is result stage. Shuffle map stage prepares the data for shuffle. Okay, like I said, I just removed the whole drawing that I did. So yeah, there's one stage where the shuffle prepares, the data is prepared for the shuffle, where like as in our example, it groups for every single partition separately first, right? And it prepares for the shuffle. And that stage is considered as shuffle map stage. And after later, when this data gets repartitioned and assembles in one executor, and that produces a result, and that stage will be called as result stage. This is shuffle map stage, and that is result stage. Remember that these are, you have to remember these names of these concepts because they might be coming in your interview questions. Okay, we're done with the stages. Now talking about the tasks. These are like micro executional jobs. I mean, smallest execution of, what to say, job or a task. Oh, well, it is named task. So yeah, processes exactly one partition. One task processes exactly one partition and runs on exactly one executor core. Not one executor, but one executor core. And one executor can have multiple cores, by the way. Remember this. We will talk about these cores when I install PySpark using Docker. We are going to define how many cores that particular executor has, and then I will talk about what these cores are. So remember the word runs on exactly one executor core, not one executor, but one executor core. One executor can run multiple tasks if the executor have multiple cores. Is retired independently on failure. It retried, sorry, not retire, it is retried. If one task fails, not all the tasks will retry. Only that particular task will retry. The rest task just stays idle. I mean, I don't mean idle. They just go independently. They don't depend on the other task to execute. And this is the pyramid, the whole pyramid. We write the code, which will then be converted to logical plan when we run it. Then after a trigger is executed or after an action is executed, that triggers the execution. And this logical plan will then be converted to physical plan by the catalyst optimizer, which is optimized by catalyst optimizer. We'll talk about it later, but yeah. Physical plan will then be creating jobs, and jobs has multiple stages, and one stage can have multiple tasks. And to represent that in the best way, I created this conceptual diagram, which on top of the pyramid there is action. There is action. When we run an action, that triggers an execution and creates jobs. And this action creates the jobs. And like I said, a job can have multiple stages, right? A job can be partitioned into multiple stages, and multiple stages. One stage can have multiple tasks. And these tasks can be distributed independently to executors. If there are, let's say, three tasks in one stage, two tasks will be assigned to one executor. Sorry, I think I messed up. I did not messed up fully, but I just messed up the last part. Let's say we have three tasks in one stage and we only have two executor cores, okay? What happens here is one task will be executed to one executor and the other two tasks will be assigned to the other executor core, which is this one. In this scenario, we are just assuming one executor only have one core here, and that's why it can only be assigned to, it can only process one task at a time. And when these tasks are assigned to this executor, if this executor only have one core in it, it only executes task 0 first, and task 2 will wait for task 0 to get executed and then task 2 will execute. So until then, it will be in the queue, basically like a queue. Yeah, that's it. That's how the flow works. I think you got that. Moving on. Here in this topic, we also have a lab. You might wondering, we haven't even installed the setup. We haven't even initialized the setup yet. Then why do we have lab here? We have lab here because I have to demonstrate how these execution units works when we run an action, right? So that's why we have lab here. But the reason I did not put the phase of installing the Spark before this phase is because we have to know the Spark architecture before we actually install it, because we're not going to use Databricks here for the installation of Spark. We are going to install PySpark or install Spark using Docker. To install Spark using Docker, we have to know what we are doing, right? And to know what we're doing, we have to have an idea of Spark architecture. And that's why that installation phase is after this Spark architecture phase. But yes, if you are comfortable to learn about these topics after the installation phase, you can just skip, or no, just skip to that part, the 2.2 topic, and then come back to this topic after the installation. That will clear all your doubts. Okay, to start with the lab, I'm going to show you this one. So this is how we're going to install. We will install 3 containers. We will initialize 3 containers. One says Spark master and the other 2 are Spark workers. You might get confused with the name. Spark master is not actually the driver. Spark master here refers to cluster manager. This is the cluster manager, and these 2 are the workers, nothing but executors. And where is the driver? Driver will be driver is not mandatory to be created as a container. What we can do is when we initialize or when we create a PySpark session or Spark session, we can define a worker as a driver. So what happens is whatever the worker we define as a driver, that will act as a driver and also an executor, whereas the other worker only acts as an executor. That's how it works. We just choose them. No matter which one we choose, we just need to choose one. Coming to the lab part, I'm going to open PowerShell. Now I'm going to create a PySpark session here. And to do that, I'm going to run. Let me zoom this in so you can see this thing clearly. Docker. Execute. And because our whole infrastructure is running inside Docker containers, we have to start our command with docker execute, and then it goes like the driver. Here I'm defining the driver as Spark worker 1. This will act as both driver and the executor. And the other one, Spark worker 2, will just act as executor and not the driver. And by the way, this file, I'm navigating to this file, this is nothing but a bash file. You just can navigate to it when you initialize the Spark cluster inside Docker. Here we are navigating to that to create PySpark session. If it is a Scala, it's a different bash file. There are multiple bash files in that. But for PySpark, we are going to use that. And then I'm going to define the master, the actual master, which is cluster manager. Now, when I run this, I talked about this part already, right? And here, to define the master, I refer to the listener port of that master. And for here, master, when I initialize it, I'm going to use this port as a listener port, 7077. So when I define it here, I have to refer to that port, Spark master 7077. Now when I run this, this will create a Spark session for me where I can run PySpark code directly on the command line interface. I'm not going to use any fancy notebooks here, but if you want to, you can. You can use even Jupyter notebook that is in your local PC, or else you can just write the code right here if you're comfortable. Either way, it works. And the real reason I'm not using Databricks here is because Databricks is no longer offering to create a free normal cluster or normal compute in the Databricks free trial account. We can create a Databricks free trial account, we can get access to it, but we cannot create an actual normal compute in that, which means we don't get, if we cannot create a normal compute, we don't have access to Spark UI. But here, because it's a masterclass, we need to know the internals of Spark. Without Spark UI, we cannot monitor the internals. And that is the reason why I decided to create or set this thing up in my local PC using Docker desktop or Docker. You can do this, or if you have access to any cloud provider like Azure, you can just use that account and create the actual normal cluster in Databricks instead of doing this on your local machine. But this is free. This doesn't need anything. You know, you don't need to worry about the credits going away, going off. This runs on your local machine, which means this has unlimited access, and you can have all the whole control on the Spark UI. So this is that. Now what I'm going to do is I'm going to run something. The document and open this. This is a link to open Spark UI. And by the way, if you even open this link before starting a Spark session, this will not open. You have to start the Spark session before you open this. Only then you'll get access to this. And here we can actually see what jobs are created, what stages are created, and basically everything you need to know. I will deep dive into this when I install in the installation step, but for now, I'm going to show you how these jobs get created here. Okay. Now what I'm going to do is, I'm going to first create the data that we are going to use. run it. We run an expression already, right? But if you even refresh this, no jobs get created because that is not an action or a Spark action. So that doesn't create any jobs. And then now I run this line. So let me edit that. It's not SF, it is DF. Syntax error. Okay, I know what's going on here. We haven't, I haven't closed this double quotes here for the value. That's error. There you go. Now I run it. Even when I run this, this is the expression to create a data frame, but even when I run it, this is not a Spark action. So that doesn't create any job. Refresh, no jobs get created. Now let's see what I actually did here. In the first line, what I did here is I created a variable which is a list of tuples named data. This is the name of the variable, and list of tuples using this. And for every tuple in the list, the first value will be I modulo 10. And what is I? For I written this loop for I in range of 1 million. So it goes from 1 to million. And you might wonder, if you don't know, why I separated this with underscore. This still is same as we writing just zeros and not including underscores. But I included underscores just for the readability. You can write both ways, without underscore and with underscore, that doesn't matter. But here, this is a lot easier to write it as a million. You can just type in this one as well, just for the context. You can just say like this, and that executes in the same way. Okay, now we define that loop. So every value from that 1 to million will be divided by 10, and it returns the remainder. And that is why we use I modulo 10, and then comma I, which is the actual value. I use this to actually separate the data into 10 equal parts, because this one will be the first column. This produces only 10 unique variables from 0 to 9, because 1 modulo 10, I modulo 10, and the data here goes to 1 million, no matter how much the data goes to. But I modulo 10, anything modulo 10 will separate the data into 10 equal parts. An integer, if the data is integer only. Okay, we have that. With that list of tuples, I'm going to create a data frame, a Spark data frame, basically using df equals spark dot create data frame of the data, which is the list of tuples which we created here. Yes, and then comma the column names. So the first value of every tuple in this list, which is this, will be assigned to the column name key in that data frame. And the second value of the tuple, which is I, will be assigned to the column name value in that data frame. That's how it works. So even if we run those two, no jobs got created. And then what we run? Then we say df equals Now we'll execute df dot show off. Remember, dot show off is one of the common actions to execute, right? It is in the list. Right here, show off is an execution trigger, which is an action. So this will trigger the jobs to get created. Now when I run this, hit enter. Well, this shouldn't happen. Let me debug this real quick. Okay, I just fixed it and I'm going to show you how I fixed it, okay? What happened is I have two workers, two executors basically, right? And those two executors were occupied with the other application. And because I already ran another PowerShell in the background connecting to the same Spark and I ran some other code. So that is occupied by the application. And that is why this task was waiting in the queue until any of the worker is available. So what I did is I went to the Spark master, which is a cluster manager, which manages all the resources, all the workers. I went to this port 8080. Here I saw the running applications. It should supposed to have only one application because I'm running one, right? But this shows two. What I did is I clicked kill on the other task that is occupying the executors, and that is why those executors are now assigned to this application. That's how it worked. And yeah, that's how it worked. Basically, this is the master UI. I will explain about this more when we install it in the phase 2, but I just wanted to show you what I did for this to debug this. I closed that, I killed that application. So here's the application, the completed application. This one, I killed it. Now this got executed. Okay, let me close that real quick. Now since that action is executed, we should be seeing the jobs getting created here. And when I refresh this Spark UI, this is what I got. This page isn't working. Why this happened is, like I said, there was another application before I started this Spark session, right? When I kill that application, this web page will also be killed. How to restore this is we just have to, you know, just copy all the codes that you have that you wrote here already, which is this. Just copy paste all the codes that you wrote. So you don't need to type them in again. And these two lines. And then these two. I don't need this. Oh, I don't need this. I need that. These two. Now close this and open PowerShell again. Okay. Make sure no tasks are running on the master. I mean, no applications are running by clicking on the master. Refresh. So there is one running. So kill that first. You kill that. Now refresh. Nothing runs. Now create a session again using this command. Now this should create an application. So you should only see that application in the master. Okay, that's good. Now run the codes again from the beginning. Just copy paste them. Oh, first open the, there you go, the Spark UI. Now the Spark UI is available and I run these two, right? And these will now not create any jobs. But when I run df dot show off, this will create a job. Now we got the output. It shows the sample records, but we have million records in that data set or in that data frame, right? And this will print a sample rows from that data frame, the df.showOff function. And what this also triggers is this will create multiple jobs, or no, one job, because it's a show off. This only creates one job. So when I refresh this, I will see the job here created. Now you know how to fix that bug as well, right? You just have to kill that application and create a new application so you can get access to the UI as well. And yeah, this here in this job section, you can see all the jobs that got created, and here it only creates one job with job ID 0, and this is the timeline, event timeline. We only ran one job right now, one job now, so that shows on the timeline here with just one right here, and it also shows the time and status as succeeded because it is succeeded. Now you have to open this job. To open that, click on the job. Inside the job, like I said, a job has stages inside it, and inside the job it only created one stage because it is a simple action, and this stage is has stage ID as 0, and the description show string submitted at time, and the duration of execution, which is 0.9 seconds, and the task that and the number of tasks that stage executed, which is just one task because that's a basic action, like I said. And input output, everything is empty because there is no shuffles executed here because this is just a normal thing and no shuffles executed, and that is why there is only one stage. Now when you open this, you can see what tasks are created and what executor this task is assigned to. And here the task with the index number and the task ID is 0, and this task is assigned to executor ID 0. The launch time, duration, everything is visible right here. This is okay, right? Now you got the concept. This is how we monitor the Spark UI. And also, you can also see the completed queries here. When I say completed queries, here in jobs, you can see multiple jobs for one action. But here, for one action, you only see one query and see how many jobs that particular query created. Here for this query, there is only one job created with the job ID 0, and it shows right here with job ID 0. And the whole query took the duration of 2 seconds to execute, to complete the execution. Now, because it only created one job, now I'm going to run another action, which is df.countof. Now this creates multiple jobs. This, what it does is it counts the number of rows in that data frame, and our data frame has 1 million rows, and that is the output it gives, 1 million. When I refresh this now, you see multiple jobs got created, and because that's not a simple action, but here multiple jobs are created. Like I said, to see how many expressions are actually or actions are actually executed, you can see it here. There is only one action executed, which is count off, and the jobs that this particular query created are 2 with the job IDs 1 and 2. When you can just click on this job and it redirects into the job, into that particular job, or you can just navigate through here. Both works. Now I'm going to show you how to navigate from here. Click on here and click on the job that you want to go. I'm going to click on the job 1. Here you can see stage, only one stage created, okay, with the stage ID 1, and the description count at, and submitted duration, it took 1 second to execute, and tasks are 4, and there is a shuffle because there are multiple jobs, because this particular query has multiple stages, and there is a shuffle. To execute this action, one stage isn't enough, and that is why we have 2 stages to execute this action, the count off. And here it created 4 tasks. Because task ID 0 is already taken by the first task that we created, the next task ID will be task ID 1, 2, 3, 4. 4 tasks are executed in this stage, and these 4 tasks are divided among the executors, and these are the executor IDs. The task ID 1 is given to task executor 1, and the task ID 2 given to executor ID 0, and vice versa. And then the duration taken is 0.8 seconds. And yes, after that we see shuffle right size. What happened here is, because we are counting them, what happens here is, when the data is partitioned among all the partitions, all the executors, when we want to count the total number, what happens? We cannot just count everything at once, right? We have to count, let's say, what exactly happened here is, we have 4 partitions for this action, right? And each has the data split among them. Let's say because we created 1 million rows, each of these executors have approximately 250,000 records, and to count them, what we have to do is, we first individually count all the records in each executor, in each partition. So let's say here it is 250k, and here 250k, and here 250k, and in this 250k, so we count those records independently for every partition, and then we shuffle it, right? We shuffle it among the executors, among the partitions, and then we create one single partition which has everything in it, one common partition which has everything in it, the data, everything that needs. But here this will only get 4 records because everything is already counted, right? And only now the output is only 1 record, which is 250,000 for everything, 250,000, approximately 250,000 for everything, and everything will be aggregated in this partition, and the final output 1 million will be given out of this partition. And because there is a shuffle happened, these 4 will be one stage, which is stage 1. Oh, my handwriting is terrible, so I'm going to use type. So this is stage 1, and this particular thing will be stage 2. Stage 2. That's how it works. So this aggregation, the final grouping aggregation will be stage 2. And to separate these 2 stages, what are the names that we use? This is the shuffle stage. This is the shuffle stage, and this is the result stage. Is that what it is called? I don't know. Yeah. Let me check that. Yeah, the first one is the shuffle map stage, and the second one is the result stage, because that is the stage that produces a result. That is how it works. Now, yeah, this is one stage which shuffle writes with only one record because it is already counted those independent partitions, right? So it only writes one record through shuffle, right? And that will be read by the other shuffle from the same query on a different job, which is job ID 2. Job ID 2, which has stage ID as 3. And this shows stage skipped because these stages are executed in two separate jobs. And because this job is already executed, which has 4 tasks, this stage is already executed at job 1. So that is indicated here as skipped stage, and it goes to this stage, which is completed stage. When we open this, we can see there is only one task because there is only one partition, right? One partition. Like I said, one task equals one task equals one partition. And here we only have one partition, so we only have one task here. Task ID 5, and that is executed by executed ID 0, and then launch time, and then duration, it took 75 millisecond. And shuffle read, so it read the data from the shuffle. That stage write the data to the shuffle. This read the data from the shuffle, which has 4 records because one record from each partition. This will read 4 records from that shuffle, and this will aggregate the final output and gives it. We will talk more about how this works in the later slides, but for now, this is enough. This is how stages, jobs, and tasks are executed, and how the stages are separated by shuffle boundaries. I hope now we got it, right? Okay, that's how you work. I also shown you how to debug that error as well, and that's why it took a little longer than usual. Okay, we are done with this lab. And yeah, we're done with this topic. Let's head to the next one. Talking about our next topic, 1.3, lazy evaluation. I already talked about lazy evaluation already, but in this topic, we will have a clear idea of why we use lazy evaluation and why. There are a few uses from lazy evaluation. There are few cases where it becomes dangerous or increases the cost of computation. The basic formal definition is lazy evaluation in Apache Spark means transformations does not execute immediately. If we write an expression, the transformation in that expression doesn't execute immediately until and unless we run an action, and that is the only time all the transformations get executed and the output will be generated. Until then, they are just logical plans. They will not be executed. And coming to the use cases, why lazy evaluation exists. First one is global optimization. Spark must see the full computation before deciding how to execute it. And the reason Spark needs to see the whole computation before deciding to execute it, the reason behind it is, unlike other tools like Python or SQL, which executes right away after we run an expression, what Spark does is, Spark optimizes the plan of execution according to the output we need, which means, let's say, in any tool, you write an expression, okay? You write an expression in first line. Let's say this is the first expression you write. I'm not going to code it because we are talking about multiple tools, right? So let's say here we are writing an expression to create a data frame or data set. Create data set 1, okay? And then you write another expression where you create another dataset. Name it dataset 2. And you write a logic where you create a filter for dataset 1 and dataset 1 alone without related to any without relating that to dataset 2. You only relate that filter to dataset 1 and name it filter with output as ds1 filter. So you filtered the data from the dataset 1 and created a new dataset with the name ds1 underscore fill. Okay, and you run an action, let's say to print the sample of that dataset. Say something, it can be show or it can be print, whatever the action is. I'm going to use show here. And say that. Now, instead of Spark running the whole thing, all the expressions sequentially, what Spark does is it only runs this line and checks if we need this expression to execute. Where in this case, we don't need to execute this, right? So Spark do not execute this. Do not run that expression or run that line, and skips that line and goes to the next line. And do we need this line? We do need that line. So we do need this line. So it executes that line and then finally prints the output or shows the output. And that is why it needs to read the whole computation, see the full computation before it executes it. So this saves a lot of computational power because we haven't done anything with dataset 2. So it doesn't make sense for us to execute that or create that dataset, right? That is just waste of computation. That is one thing. Oh, that is actually point 2, avoiding unnecessary work, not the point 1. Global optimization is separate, is different. What global optimization is, Spark won't run the expressions sequentially according to our coding plan or our logical plan that we code. So when you write this, it won't run sequentially like that. What it does is it thinks about the most efficient flow or efficient order to execute these expressions, and it follows that own order. So Spark reorders these transformations and finds out which order is more efficient, takes less computation, and reduces the shuffles. And that is what global optimization is. It optimizes the flow. And that is why the lazy evaluation is useful. These are the two use cases. And the fourth one is efficient failure recovery. Spark can recompute only what is required. That's the same thing. It ignores everything and only recomputes what is required and not everything. If something goes wrong, it only recomputes that part and not everything it needs. Okay? Which means, let's say you here in this example, I only filtered dataset 1. Yes. Let's say I also filtered dataset 2 and ran another action to show dataset fill dataset 2 underscore fill as well. And when I run that, let's say there is a failure in one of these two actions. What Spark does is it only retries the steps that are required to fix that failure and not everything. You don't create the dataset 1 again if dataset 2 fails. It only creates dataset 2 because that is only the one required to recompute the failure. That is one more application. So there are 3 use cases for this. I mean, there are 3 uses from lazy evaluation. And now we talk about when lazy evaluation becomes dangerous. There are a few cases where it becomes dangerous. One of that includes multiple actions are called. So multiple actions are called on the same data frame. And because that data frame is not those transformations are not executed sequentially. If multiple actions are called at the same time, one action executes once, okay? Let's take the same example that we used before, using the filter, all right? Now, when I run show off and I forgot the name, show off fill underscore ds1, it computes, it computes the whole thing for the data set because I call the action, but you don't catch that result or catch that transformations. So when I run another action on the same data set, let's say I say count off instead of show off, so I use two actions at the same time on the same data frame like this. So first I call show off, and second I call count off. They both are actions. So what happens here is when I call show off, this runs all the transformations that are required to show that particular thing, and say show off, let's say df data frame. So it runs everything that needs to be executed to get this df output. But you don't catch that transformations. You don't save that as catch. So if the same application runs count off again on the same data frame, which is df, what happens is the whole transformations are recomputed again because there is no catch data. And if there are multiple actions like that are executed at the same time, or that overwhelms the system because those transformations will be done over and over again. Whereas in the other tools like the other one, which executes those transformations linearly right after we write it or define it, in those systems that will be saved, and when multiple actions are called, because that is saved, they don't take much of computation, right? So that's the downside of this lazy evaluation. And the next one is expensive transformations are not catched. Spark recomputes from source every time. That's the same thing, right? And then for the third point, we have developers assume order of execution. Spark may reorder or optimize away steps. I talked about this already, right? You don't follow the order you code it in. Spark reorders the transformations according to which would be the best fit to reduce the computational power and time taken for that execution, and also reduce the shuffles. So there are a lot of reasons for this optimization, and that is one of the dangers. Developers assume order of execution. If developers assume, let's say I write the code in Spark in this order, and these transformations will be executed in that order, and that will cause a problem For developers, yes, because those are not executed in order. That is one of the problems with it. Well, the last one is not that big of a problem, but this one is, because the results of the transformations are not catched. And I also have a conceptual diagram. It is a simple diagram, so I'm going to show you that. Okay, it's a simple diagram. We write the transformations. The transformations are nothing but are used to create a logical plan. But this logical plan is not converted into a physical plan. This is just a logical plan. And when actions are executed, those trigger the execution. Then this logical plan will be transformed into physical plan and will be executed. That's it. That's it about the block diagram for lazy evaluation. Okay, let me, for the example here. Now let's do the lab for this to show, the downsides of it, because I already explained the lazy evaluation to you when I ran the other lab, which is the 1.2. I said when the action triggers the execution. But here I'm going to show the downside of it by running two different actions, which is basically which basically needs the same transformations, but two actions runs separately again and again. So yeah, let me do that. With this expression, I'm just going to create a list of tuples again, but this is just quite different. I'm just going to use I as the first value in the tuple and I times 10 as the second value in the tuple. And then create a data frame out of it. With that expression, so the first value in the tuple is the first column and the second value in the tuple is the second column in that list of tuples. Oh, that's correct. I have to import the call first to filter that. So I'm gonna import that. Don't worry about these filtering transformations, because we are going to talk about them in the later topics. But for now, let's just remember what this does is df filtered equals, so it filters out the column which is the value column to only have the values that are over 5,000 in it. So by that, so we say df.filter of call of quotes value greater than 5,000. So we are just filtering them out by the value column. We're just filtering out the rows. That now just copy paste this filter. Okay. Then run another filter. I mean, it's not a filter. We're going to select a column, just one column from that. Now what this does is, first here, it filters out all the values that are less than 5,000 in the value column, yes? Which means because our data frame has 1,000,000 records, this will take out like 5,000, I think 5,000 rows out of that 1,000,000 records. Which means after that, we only will have 999,000, sorry, 995,000. Yeah, 995,000 values or rows in that data frame. And after that, we select only the ID column and we omit the value column out. So we're not selecting that, we're just selecting ID. So what happens here is, no, you don't emit 5,000 records from that data frame, because the value here is I times 10, which means 5 becomes 50 and 500 becomes 5,000, which means it only emits 500 records. So we will still get 999,500 records as the output. And from that, we are only selecting ID column. Now we run the whole thing, but like I said, no jobs will get created because no actions are actually executed, right? Now I'm going to run dot show off. Now this will execute everything, which creates how many? Which creates one job. All right. By the way, this is the physical plan that we can see here for the queries. I think there is another topic where we talk about these physical plans and logical plans. But for now, yeah, I'm going to skip that topic. Okay, so that is executed. So when I run that, it executes everything from the beginning to the end. DF filter, select, everything. And when I run, let's say, the same thing, I'm going to run the action, another action, count of, run it. So that prints the output 999, 499. But what this does is, this again executes all the transformations from the scratch again. Because it don't save the result or the result of the transformations in the memory. And that is why it executes everything. And that creates 2 jobs. Yeah, it filters out everything again. I cannot show you how these the transformations executed, but yeah, theoretically they are executing again. So when you say instead of df underscore select, if you say df underscore filter dot show off, this only executes the transformations until this one and ignores df underscore select because we don't need that, because we're just trying to show the output of df filtered off, df filtered data frame. That's how lazy evaluation work. It is good at some situations and it is bad on the other few situations. So it depends. And now I think you got the concept of lazy evaluation. With that, we end the topic and head to the next topic. Now our next topic is 1.4, Spark DAG, logical versus physical execution plan. A DAG stands for direct acyclic graph. I think it's here, yeah. DAG stands for direct acyclic graph. Nothing but a graph, a flow of tasks that Spark follows to execute or to get the output from it. So it creates a graph or flow chart. Basically, a flow chart would be more memorizable. And the difference between a logical DAG and a physical DAG is this. Logical plan is nothing but our code. It says what needs to be done, but a physical DAG shows how Spark will actually do it to get the output. Right? When we write a code, we just say what we need to Spark, and how it works is quite different. Like I said, it optimizes the flow. It don't just blindly follows the flow that we define in the code. It just optimizes and then creates its own physical DAG or own physical plan and then follows that plan to get the output. But by the end, we'll get the output that we desire. But what Spark does is Spark optimizes it to have less shuffles, you know, make the transformation faster and stuff like that. And to differentiate between the logical plan versus physical plan, this is a table here. What it says is aspect built from. The logical DAG is built from our code. So our code is what basically the logical plan is. And the physical DAG is the optimized plan, which is optimized by Spark using Catalyst Optimizer. We'll talk about it. And then knows about transformations. Logical plan just knows about the transformations, not the physical components that are needed to get the output, right? That's what it says. And the physical plan knows about shuffles and stages. It cares about shuffles and stages, right? What it means is when we write a code, we just say group by and do this and do that. Group by or join that or just count that. We just say to do that transformation. But what physical DAG does is physical DAG separates that jobs or the tasks according to the shuffles and stages and then segregate them so it can execute to get the desired output for us. And that is all done by Spark. We don't do that. And executor aware, no, it is not aware of executors, whereas physical DAG is aware of executors. Because physical DAG is also has to include the partitions in it, so it has to be aware of the executors. So it has to know how many executors are alive and how many threads each executor has, so it can divide the work among them. Determines performance indirectly, directly. It also logical plan I mean, our code also determines the performance, but indirectly. But physical DAG affects it directly. That's the difference between the logical DAG and the physical DAG. Now, talking about the catalyst optimizer, what catalyst optimizer is, when we run a code, the logical plan will be created, like I said. But before turning the logical plan into a physical plan, what happens is Spark uses a catalyst optimizer to optimize the logical plan to create the physical plan. What it does is, before execution, Spark applies catalyst optimization to the logical DAG. Catalyst can reorder filters. It reorders the filters and the transformations according to which would be the best way to reduce the shuffles and make it faster to execute, stuff like that, and push predicates closer to the data source. Now, what is predicates? What are predicates? Predicates are the one. Let me explain it with an example. Let's say you're working with a data set. Okay, you're working with a data, and you only want a small chunk of that data to actually get the output. Okay, so what Catalyst Optimizer does is it don't just get everything, all the data to get the output. Instead it only gets the required data from the data source to actually get the output. That is what predicates are. It only gets the required data. Eliminate unnecessary columns. It don't consider the columns that are not necessary. It only consider the necessary columns. Combine compatible operations. Catalyst cannot remove shuffles, fix bad partitions, optimize opaque logic. It don't do that, but it reorders them to optimize the flow. It don't remove the shuffles, by the way. It just optimizes to minimize them. Wait a minute. Uh, yeah, that's correct. But it don't remove the shuffles, but it optimizes to have less shuffles. Now let's do the lab for that. Let me open the PowerShell. For this, we need, and by the way, all the labs and all the things that stuff I'm doing here, you can get this file from the GitHub link. So don't you worry about the labs, okay? You can get the whole material, by the way, from that link and follow the labs along with me. You can just copy paste the codes that I'm writing by myself here, but you can just copy paste them and run them to see the Spark behavior. And also for the installations, I will also give the docker compose.yml file in the same GitHub link, so you can get that as well. Okay, we have that from PySpark. So we import Spark session here. Then from then we also import the call. We use the same list of tuples that we defined in the beginning. It should be I. Range of 1 million. This will create a list of tuples which is divided, which is separated into 5 keys basically. We create a data frame out of it. Like that. That expression creates a data frame. There you go. Now I do some transformations with filter and groupBy. I run this one. Is that correct? Yep. Oh, this should have a closing bracket, parenthesis at the end. Okay. And with this transformation here, what we do here is, first we filter out the rows with the column value to have the value greater than 1000, which means the output will only have 998,000 records, and then we group them by category, which then will be reduced to 5 records because we used I modulo 5, remember? And when we use I modulo 5, the data will be divided into 5. The data will be in the range of 1 to 5. Oh no, 0. Sorry. Will be in the range of 0 to 4. Okay, and that is why this, when we group by category, this will categorize them, this will group them, and the output rows will be just 5. And then we use dot count of as the aggregation factor for the other column, which is value. We group by category and we use aggregation on value. So the output we get will have 5 rows where value will be counted and category will be grouped. I think you got it. Now, I run this. This will print the physical plan right here, but still this won't create any job. This will not create any job, but it shows how these transformations will be planned as a physical plan. We can see that before so let's say if you're working for a big corporate and you write a huge application with multiple transformations and you don't want to run it without checking the physical plan. How you can do that? Well, you can find the physical plan when we run an action in the Spark UI, right here. When we open the job and extend the DAG, we can see the physical plan here. But if you want to see the physical plan before you run an action, this is how you can do that. You can just write df of df result underscore df dot explain of. So this will print the physical plan, which you can see and proceed if you like the plan, or you can change your logical plan, which is your code, if that is not satisfied. You are not satisfied with the physical plan. Here, this is the physical plan. It goes from the bottom to the top. So the first one will be this: scan existing RDD, filter them, project, hash aggregate, exchange, hash aggregate, adapt to Spark plan. This is the physical plan. So when I run an action, that executes the exact physical plan that is created. So let me run an action here and say show off. You see, like I said, the output will be 5 rows with category as grouped and count as aggregated, which is count. Using aggregated using count as the operator. Now when I refresh this, we can see another wait. And here we see 2 jobs getting created, which are with job ID 6 and 7, these 2. Yep, these 2. But when we go to here and open this, which is show string, here we can see the physical DAG. And let's compare this physical DAG of our query after execution to this before execution physical plan. Starting from the bottom, scan existing RDD, filter, project, hash aggregate, then exchange, and there is a shuffle read, and then there is a next hash aggregate again, and later there is adapt to Spark plan. The exact physical plan even after execution. That's how you can see the physical plan before execution by running that command. And now with that, we know how the logical plan and physical plan are created, and how the catalyst optimizer work, right? And how we can check the physical plan before executing any action. And with that, we're done with this topic, and let's head to the next topic. Now heading to our next phase, which is phase 2, Spark setup. But it starts with the topic 2.1, which basically says why I use Docker instead of Databricks. Well, Databricks free trial doesn't, like I said, I think I already talked about Databricks, why I haven't used Databricks and why I use Docker, but I'm going to say a brief things that I observed in Databricks that are changed. Okay, in previous versions of Databricks, basically the free trial, in free trial, they used to allow users in the free trial to create a normal compute and run jobs in it. So you can open a normal compute with multiple, machines and run on it. But in the newer version or newer free trial accounts that we take, we are not allowed, or we are not allowed to create a normal compute. But Databricks offers a serverless compute. You can still run Spark jobs or Spark code in it, but the actual thing here is you cannot see the data distribution among the partitions, and also you cannot have access to Spark UI. Spark UI is, in my opinion, it's so important to see the internals of Spark and how that particular action or execution is happened behind the scenes of Spark, because that's the whole point of learning Spark. Because Spark is not like any other tool like Python or SQL. We have to see the internals here, because the main point of this is distributing the data across the partitions, and that is why even until now for every lab we are monitoring the Spark UI, right? This is the Spark UI. We are monitoring for it for every lab. Well, if you use Databricks, you don't have access to it, free trial, unless you have a free trial account or you paid for any of the cloud provider like Azure. You can have access to Databricks and you can create, a normal compute in Databricks and then run it right there itself by creating notebooks. And you will also have access to Spark UI. You can see the jobs running live, and task split it all across the executors and everything. You can actually see that because Databricks is a managed space for Spark and optimized other optimized tools. So you can do that if you have access to any of the cloud provider like Azure or I think AWS or GCP. But here, to make it practical for you guys to have access to everything, unfortunately, I would not recommend Databricks free trial to learn Spark because that has a limited access. And that is why we're going to create Docker, which has full access to Spark UI, and it is free. No matter how long you work with that, you won't get charged anything because that's a free tool. And that's why we're going to set up the Spark using Docker containers. That's the main reason. And yes, with that, our topic 2.1 is done. Now let's head to the next topic where we actually set Spark in our PC or inside the Docker, basically. Let's do that. And this topic is about installing Apache Spark on our PC. And there is a prerequisite you have to install before we go further, and that is Docker Desktop. So to install it, you just go to any web browser and search for Docker Desktop download and click on the first link, or you can just click on this download link if it appears. Or else what you can do is you can just click on the link that I will provide in the description that right away goes to this page. From here, click on download Docker Desktop and pick your appropriate option according to your PC, and it depends on it. So yeah, click on it and download it. After install it, install Docker Desktop with all the default settings. You don't have to change anything. Install it and open it. And when you open it and skip the sign up process, or if you sign up, that's fine, and you will land on this page. Okay, you land on this page. Right now there are no containers running because we just opened it, and I closed the containers that I opened before. So I'm going to show you how to freshly install everything from scratch. This is the pane where we can see the containers that are created in Docker. Okay, let's minimize that. Now let's have a look at the Docker Compose code that we are going to execute. This is the Docker Compose.yml code we use to initialize the Spark setup on our PC. The first one is a version 3.8, okay. And the services include the first one as Spark Master, which will be our cluster manager. We have to initialize that first. Cluster manager with Spark 3.5.1 and then command bash operator, and we use this to deploy master, and then we define two ports, okay, and for the those two ports have their own different uses, and the port 8080 will act like our Spark master UI, which I opened before. That will act like Spark master UI. We can open Spark UI using that port on our web browser. And then we have 7077. This is a Spark master port. When we open a Spark session, we can define the master with this master port 7077. That's how we create a Spark session with this master. And these are the volumes. When we create a container in Docker, we can define a few volumes. And the reason behind that is when we create a container in Docker, it works as a different environment or different machine or something like that. So that container won't have access to the files in your computer. But to give access to those files, what you have to do is you have to define the volumes using this. And here I'm going to define two volumes, one for apps and one for data. But basically I only use data to actually, use that space when I write the data, or when I write or create a file like CSV or JSON. To write the data, I'm going to use this volume. This apps volume, I'm not going to use it, but if you want to use it, you can just keep it as secondary. Or you can just take that out. That is still fine. So that's what basically the volumes are. You can write and you can also read from those volumes. So it is like back and forth operations. It's not just about writing, it is also about reading too. So it basically has access to those volumes. That's it. Now we define Spark worker 1, the first worker. One container for that with Spark, of course, 3.5.1 and Spark worker 1 as, and the command has the Spark master port, because this is the port we can use to connect to the master, right here, Spark master port 7077. That's how we use it and connect this worker to that master. And this worker has two ports, and they also have their unique reasons. Okay, for the first port, which is this, is nothing but the worker port used to connect to the worker, and this port 4040 is for the Spark UI. And I defined this port because I'm going to use this worker as a driver as well. When when we create a Spark session, a PySpark session, I'm going to define this worker as a driver. And if I define this worker as a driver, it should also have access, it can also have access to Spark UI. Yes, and this is a port we can use to connect to the Spark UI 4040. If you already watched the topics 1.2 and 1.3 or 1.4, you already saw me using this port to access Spark UI. Okay, that is that, and depends on Spark master, depends on that container, and the volumes. It will also have access to this volume, so it can write those partitions. And the same thing repeats for worker 2. The only thing that changes is it only has one port, because this will not act as a driver, so it doesn't need a UI. I mean, it doesn't need a Spark UI again. Yep, that's it. And it is also connected to 8081 because this is just a normal executor. This is an executor and a driver. That's it. From this, we are going to create 3 containers. To actually create these containers in the Docker desktop, we have to save this code first. So I'm going to save this code first. Copy that. You don't need to copy that from any Word document. I'm going to give you the whole docker compose.yml file itself in the GitHub. So you can just download that file and use it. Paste it here. See, when we copy paste it from a Word document, the code, the new lines gets added into the code, and I don't like it. So what I'm going to do is, I'm going to get the code from another file. Let me get that. Okay, now I have the code ready. Now what we're going to do is, we save this file in a folder. Let's say in C drive, users, username. I'm going to save it here. I'm going to create a new folder first. New folder with the name Spark Docker. Open that. Here I'm going to save it as docker hyphen compose.yml because that's a YML formatted file. And here change the save as type from text to all files. UDF8, save it. We have the file. Now open Docker desktop. Open that. Click on the terminal at the very bottom on the bottom right. Click on that. Let me open a new window. So, yep. Now navigate to the folder that we created the docker compose.yml file. Right now we are at C drive users and the username, and inside we created a folder named Spark Docker. So we say cd change directory Spark Docker. Spark Docker. Now we're inside that folder. Now here, this is the location where we save docker compose.yml. From here, we say docker compose up and -d. What we're doing here is to create the containers, to start the containers, we run docker compose up from that folder where the docker compose.yml file is saved. And to close the containers, we run docker compose down. To stop the containers, or to delete the containers. To delete the containers, we run docker compose down. To start the containers, we run docker compose up, and -d is a flag that stands for detach. Without -d, if I run this terminal will be dedicated to show the logs that are happening in those containers. When I run -d, it don't show any logs. It just goes to the next. It just pass that and asks you for the next command, like that. So it asks you for the next command. Now, when we run it, we have to see these things here running 4x4. Network Spark Docker default created, container Spark master started, and container Spark worker 2 started, container Spark worker 1 started. Now collapse this. Here you can see those containers getting created in the UI itself. Inside this folder, and these are the container names. Now to inspect these containers and make sure they're working, what you have to do is, for Spark master, we defined two ports, one for the UI, remember, open that port. Now, you know what, first let's open the workers port first. So we have for worker 1, click on show all ports, click on this 8081 port, click on that, that will open this. So this is the Spark UI. In this is a Spark worker UI. This only shows the running executors. So this basically shows the actions that are, the processes that are going on in that particular worker. Now let's open the other workers UI, which is this. So this, yeah, that's the same thing. So there's nothing new to talk about. Okay, and we open the Spark master UI, which is 8080, port 8080. Click on that. This is the master UI. This shows all the connected workers to that master. Right now we have two workers that are connected to this master, which includes these two workers, because we defined those two workers, and this has everything that is related to those workers and also the running applications and the completed applications. Applications are nothing but us creating Spark sessions, and when we close the session, that will be listed under completed application. When we are still running the session, that will be listed under running applications. We will see how that works when we actually run a Spark session. Okay. Yes, for every worker, it shows the address, the IP address, and the state. If it says alive, it is active. If it is not, it says inactive. And the cores that each worker has. And this worker has 2 cores and 0 used because there are no tasks or any applications running. So 0 cores used, but it has 2 cores. And here it has 2 other cores for this worker. And the memory, 2 gigabytes for each of them, and 0 bytes used from that. Now, talking about the cores, you have to know something about the cores here. Cores are nothing but threads. Let's say in this situation, in our case, we have 2 cores for each worker, yes, which means 2 threads that can be handled by each worker. So 2 plus 2, which is 4 in total. Now, for this Spark cluster, if I run a session and if I run a transformation and then run an action, what happens here is this, when I explain it in the right way. Okay, let me draw something, okay? Let me draw something. Let's say I executed an action, then that created a job, and in that job, there are like, let's say 6 tasks created, okay? 6 tasks. Say, no, 1, 2, 3, 4, 5, 6. 6 tasks created. What happens is, because our workers have total of 4 threads, 4 of these tasks can be executed at the same time, parallel to each other. Okay? Same time, parallel to each other at the same, and the rest of the tasks will wait in the queue until one of these workers gets free, and then this other task will execute. That's how these cores work. The number of cores is equal to the number of threads, and number of threads equal to the number of tasks that can be executed parallelly in that particular worker. We have 4 threads in total. So if we have 4 tasks created by an action, we are good. We are just, those 4 tasks will be executed parallel to each other and we'll get the output instantly. That's how these cores work. And the memory, we already talked about the memory. It stores, instead of going back and forth with the disk, it just stores the data, the intermediate data in the memory. And that is why it uses the memory here. Yeah, and that's it. That's it with that, but we cannot open this Spark UI from the the driver work, from Spark worker using this port 4040. If we open that, this pops up. The page isn't working because we can only access to that Spark UI when we actually define the Spark session with the driver as Spark worker 1. And how we can do that? We can do that by creating a PySpark session or any Spark session. And to create a PySpark or Spark session, we have these action already, right? Now, when I run that, this creates a PySpark session and defines that as a driver. And now, when you access to this port, this will be visible. You can actually see the Spark UI here because the driver is defined and the Spark session is active. And yes, that's how the installation works. I think you get everything. And you followed me and get the infrastructure ready on your PC. Because when we go to the next labs, we need this setup on our PC. Okay, with that, we're also done with this topic, which is the installation of Spark on our PC. Let's head to the next topic. And our next topic is 3.1. This is phase 3, by the way. We're going to talk about data ingestion. And our first topic will be the Spark Data Reader API. So Spark has its own data reader API. Till now, the examples we saw, I just created the Python list of tuples as our data, right? The Python list, and then I converted that into a Spark data frame. But now I'm going to explain how we can ingest the data from an external source into a Spark data frame using Spark Data Reader API. Basically, in Spark Data Reader API, we abstract all the configurations in 3 types: data source, information about the data source, the location of it, the format of it, and the logical schema. Schema is nothing but the structure of the data that it has to be loaded as, and distributed scan. If you don't know what schema is nothing but the data that we get. Let's say if we get the data from CSV file, we have multiple columns in that schema, yes? It is nothing but, the data structure. Defining the column names and defining the columns data types, and then assigning that logical plan, basically the plan of that data structure, which is a schema, to that data that we just ingested. That is what a schema is. And this is the basic format to write a Spark.read reader API. To read an external source, we say Spark.read.format. Don't worry about this, the forward slashes. Those are just define the new lines. You can just write this whole expression in one single line, but just for the readability, we just separate them in different lines so we can read it in the right way. So these forward slashes are just for the new lines. You can just instead of writing like that, you can just write it right next to it, like that. Okay. So yeah. So the order that we configure this read is not uh, mandatory. This is not the order. You can order it anyway, but it has to contain format. You have to define the format of that external source. It can be a CSV, JSON, or Parquet, whatever it is. We define the format with dot format of and double quotes and the format name. If it is CSV, we write CSV there. And talking about dot options of, well, these three, the other three, like this block, dot format and dot schema and dot load of, they're all common in most of the external sources, in most of the read expressions. But options are the way that allows us to configure the read. We can configure the read. Oh, there it is. So we can configure the read time behavior using options. There can be multiple options. And these options, there are a lot of options, by the way, and these options can be, depends on the format of the data source that we are ingesting. And we can configure that, and we can use multiple options in one single read expression. Whereas the others, we can only write one of them, because that doesn't make sense to write multiple of them, right? Like the format, we just need to define it once. If it is CSV, the whole thing should be a CSV. And the schema, once. And also the load path is also once. But options can be multiple. According to, it depends on our configurations and our wish. And here, the dot schema of is where we define the schema. We can create an external schema. We define an external schema and assign it to this, or we can just use something called infer schema, which Spark automatically assigns the schema for the ingested data. We'll talk about these schema types later in the later topics, but yeah, that's what schema is. It's basically a plan of a plan that we say Spark to make the data, to structure the data in the right way. And dot load of is where we define the location of that particular external data source. This is the basic format, basically the syntax. And these are the supported data sources that Spark can accept, which includes CSV, JSON, Parquet, ORC, Avro, Delta, JDBC. As far as I know, we mostly use Parquet for big data. Parquet or Delta. Delta is a format, Databricks native format. It's not a file. I mean, it's not really a file format. It is kind of a structural format. It uses Parquet mostly, and it saves other files. But yeah, that is Databricks native. But this is a PySpark masterclass. We're not going to include that. Yeah, Spark will accept these file formats. I mostly use Parquet, and in some cases I also use JSON, where we can, because JSON is more configurable. So I used, and I mean more easier for to create, and I mean to create it, not to read it though. To create it, JSON is a lot easier. But Parquet is the fastest among all the rest. I think there is a top. Yeah, our next topic is about the file format. So I'm gonna talk more about the file formats in the next topic. And talking about the Spark Reader API, it is also part of the lazy evaluation. It will not be executed until an action is performed. You might think, because this is a reader API, as soon as we run the expression, you might think that will be executed. But now, Spark only reads the data using the reader API only when there is an action that calls to do that. I mean, to do so. So when there is an action like show off, count off, or collect off, or write off, that is executed only then if that particular external source should be read it to get that output. That is the only time Spark starts reading that data from the external source and do that, the transformations, and give the output to it. Yeah, just to confirm, that is not part of an action. Read Spark.read is not an action. It is also part of the other transformations, basically. And I also have a conceptual diagram for that. There it is. So here's the thing. So first there is external storage where we store the file, the data at. So that is this is the location, and then we use a data Spark data source reader implementation. We implement it, and the logical plan schema. We only have logical plan till now. Even if we run that expression, the data reader expression, only when we trigger an action, when an action is triggered or executed, that is the only time when the logical plan turns into a physical execution plan. And if that action calls that to, I mean, to satisfy that action, if we need that external data source to be read, that is the only way that data source will be read, or else it will be ignored because of the lazy evaluation. Yep. Now let's head to the lab for that. For the lab, for this one, the data reader API, I'm going to create a CSV file and then read it and show you how we read a CSV file. So I'm going to open the PowerShell again and create a CSV file first and then read it back again. Now here, I'm creating a Python list of tuples like we did before. Until now, there is nothing to do. There's nothing for Spark to do with this variable, the data, because this is just a Python list of tuples. But now we are going to convert that list of tuples, the Python list of tuples, into a Spark data frame, and that is where Spark takes the work into hands. Before that, no. Yeah. Let's do that. So this expression will create a Spark data frame, and this is what Spark actually bothers about. And the rest, this expression, this is just a Python list of tuples. So this has nothing to do with Spark. This is just a Python list of tuples. Now when I run this, this will create an actual Spark data frame, and from now on, whatever I do on this data frame, Spark does it. Spark Spark is responsible to do that. What I did here is for all the tuples that are in the list, the first value in the tuple will be assigned to the ID column for the data frame, the second value to the name column, and the third value to the sign up date column. I basically want to create a list of customers with an ID, a unique ID for every customer, and a sign up date, a random sign up date for them. Now I'm going to convert this data frame into a CSV file and store it in an external location where I will write the read expression again using Spark, and then I read the data. But right now, don't you worry about what I'm doing in this expression. I'm just creating the CSV file because we have a separate topic where we talk about the data writer API, Spark data writer API. But now we'll just skip that. What we're doing is we're just converting that data frame into a CSV file and storing it into an external location. That's it. I ran that, which means that file should be now saved into the external location right here. And the reason the file got stored in this location is I basically defined this as the location opt/spark data/users_csv. And if you remember, when we defined the Docker Compose file, the containers, we defined these as the external locations, the volumes, which those containers have access to. Remember? And that includes opt/spark data, which is dot data. Because I ran Docker Compose from this location, this particular location, when I ran this code, it automatically created these two folders. If there are these folders already created in that location, you don't create a new one. But if there aren't any, Docker creates these folders for us. Now, this is the location, this is the external location, and this is how it will be mapped through the container opt/, but this is the actual location dot/data from here. So /data and /apps. I used opt/spark data, opt/spark data /users_csv. That is the location that CSV file needs to be saved. And now when I open the data, we don't see one .csv file. And the reason behind that is because Spark is a distributed system and when we write something, by the way, read is not an action, but write is an action. Whenever, right after we run the write expression, a job will be created. Let me refresh this. There you go. A job will be created which saves a CSV file in the desired location. And that tasks will be splitted across the executors, and each executor writes the data from its own partition. Yes, and without us externally or manually customizing that to combine that partitioned data, the data will be separate. You see that? In this folder, there are multiple CSV files you can see here. This is basically same as us having one CSV file. But what happened here is this data, this write operation, this write action is distributed across 4 partitions basically, and 4 of those partitions write their own CSV file, write their own output as a CSV file in that location, and that is why there are 4 CSV files. And if you open that, each one has one record in it. See that? One in that, one in that, and the first one only has header, because all 4 of them just separated that or partitioned that data and or distributed that data among them, and that is why there are 4 files. We will talk more about this later when we talk about the writer API, but I just want to show you how this works. And we'll talk about these files later, okay? But for now, just assume this as a normal CSV file. This is not a fold. Right now we see the folder, but just assume it as a normal CSV file. It works exactly the same as normal CSV. It don't works as a different CSV. I mean, different file. So yeah. Now let's read it. D of equals. We use, what's the format? Spark dot read. And now starts the configuration where we say format. Say format dot format of, and the format that we saved is CSV. So when we read it, we have to define the format as CSV. So the Spark will know that is a CSV file. CSV, and then dot again, option, header, like I said, we can use multiple options, and these are just the configurations that we can use. And what I'm defining here is I'm saying our data does have a header. So we are just making sure Spark will not read that header as a separate column. You understand that, right? So every column has its own header, but Spark doesn't know that. We as a human, we can read that as a header, but Spark doesn't know that. Spark might take it as part of the row. So defining header is true with the option. We are saying Spark, there is a header in that data, so exclude that first row out as a header. Just read the data. So now Spark only reads the data and excludes the header. That's how it works. And use another option, say because this is just about reading Spark Data Reader API lab, we're not going to define any schema. Schema is a separate topic. So for now, like I said, we can use infra schema. Just when we don't want to define a schema. So right now we don't want to define the schema just because we just want to demonstrate how data reader works. So I'm going to use infra schema. So Spark defines a schema on its own automatically. And for that we use one more option. Because we already used that option to define the infra schema, to define the schema as infra schema, we don't do that other thing where we define the schema in format. Remember, we have this line. So we exclude this line because we already defined the schema as infra schema. We exclude this line and go to the next line, which is load, where we define the path. So now we define the path dot load off, and the path is slash opt slash spark data, and the CSV folder name, the folder name where all the CSVs are saved, which is users underscore CSV. Because we created a folder of CSVs which are partitioned, we just point to that folder, not each of those CSV files or each of those separate CSV files. If we want to directly point to a CSV file, let's say I have a CSV file saved as users.csv, I'll just say users.csv. I point to that file directly and not the folder itself. But right now we have a folder of CSV files and everything, all the CRC files are also configured. We will talk about CRC files when we write the data, but for now we're reading that, and hit enter. Now we read the data and we used the automatic schema assignment by Spark by using option infra schema, and then we define the format as CSV. So now all the data in that CSV is given to the data frame df. It's now saved as df. Now, like I said, spark.read is not an action. Even if I run that expression, no extra jobs will be created. Right now I only have job ID 0. Yes. If I refresh this page, so it just loaded, I think. Well, it did create a job, but you know what? Let me just run an action and show you what happens. Say df dot show off. So this will show a sample data of that data frame. Because this data frame is very small, this will print the whole data frame basically. Let's run that. Yep, this printed all the records. Now if I refresh this, now this will create 2 jobs. Okay, now I found the reason why this job got created. Let me explain. So this particular query got executed when we run the read expression, yes? And the reason for that is, if we just run a normal read expression, no job will get created unless we define something called infra schema. Remember, infra schema is telling Spark to automatically assign a schema to the data. And because that infra schema, and we are saying Spark to automatically assign a schema, Spark needs to read the data first and then decide what schema it needs to assign to that data. And that is the reason it created this small job, this small job. That is what it did. It scans the text and decides the schema. That's it. And only when we execute an action like df.showOff, that is when it actually reads the data to process the transformations. And here it created two jobs. This is the query to show the data. Here it created two jobs. Just like that, we have the output here. And with that, we're done with this topic, Data Reader API. Now let's head to the next one. Now for our next topic, we're going to talk about the file formats, the mostly used file formats. Just knowing about reading those files from an external source is not enough. We have to know how those file formats work. They all have their merits and demerits, and we're going to talk about them. And for this topic, we're going to talk about CSV, JSON, and Parquet file formats. All three of them have their own characteristics. To compare these three formats, I actually have a table. Okay, so here we have 4 columns. First one is the aspect, and we compare all the file formats with these aspects. And the file formats are CSV, JSON, and Parquet. First thing, storage type. For storage type, CSV and JSON store the data in rows format, whereas Parquet stores the data in columnar format. If you're confused about this, I'm going to explain it, okay? While CSV and JSON saves the data as rows format, like we just wrote a CSV file, yes? So I'm going to open that and show you how they differ. I have to pin this folder to, yep, data, CSV, and open that. You see that? It saves it stores the data in rows format. It saves the data in rows, the whole row, like that. That is the CSV, and that is how CSV and JSON saves the data. Whereas Parquet, it saves the data in columns. Where CSV and JSON save data as rows, Parquet saves as columns. And there is a unique advantage of saving the data in columns, and I'm going to talk about that as well. And the use of it is called something with the name column pruning. I'm going to talk about that, but for now, let's go to the next aspect, which is schema. Schema for CSV and JSON should be externally defined when we read it, because you remember when we read the CSV file in the last lab, we use the infer schema, so we're defining some sort of schema when we read the CSV file. And also for JSON, we also have to define the schema, or we use infer schema. Whereas in Parquet format, the schema is embedded. The schema is stored within the Parquet itself. We don't need to define the schema again when we read the file. That is one of the unique characteristics for Parquet. And compression. CSV has no compression, and JSON no compression, whereas Parquet, yes, Parquet is compressed. You might not feel the difference when we work with the small scale data, but in high scale, I mean, when you work with the high scale data, well, the big data, you will feel the difference. You will feel the massive difference between saving the data in CSV format and saving the data in Parquet format, because in Parquet, the data is compressed. It takes less storage space. Now, talking about column pruning. This is the major upside of Parquet and the way it stores the data, the columnar format. Basically, what column pruning is about is, there are a few transformations where we only want one column to pick. Like, well, in what I mean is, there are a few transformations where we only use one column for that transformation and not the whole row, right? Something like creating a new data frame by picking one or two columns from the data frame that has multiple columns. Yes? In that case, you don't want to read the whole data frame. You can just, if you use Parquet, and let's say your data frame has 3 columns, right? And you only want to create, you are going to create a new data frame out of this data frame, and you only want this column. What column pruning does is it only reads this column from the data source, okay, from Parquet. So it only reads that column and it avoids the rest of these columns, these two. It don't read these 2 columns. It only reads this column and creates that new table with that column. That's how column pruning works. It avoids reading all the columns when we only need one column. Whereas in CSV and JSON, we cannot do that because they are stored in rows format, whereas Parquet is stored in columnar format. That is one of the major advantage of Parquet. And predicate pushdown is the other aspect. It is almost like the column pruning that I just explained. But this is not just about columns, this is about the data. Instead of reading the whole file, what predicate pushdown does is it just connects to the data source directly, and it only reads the data that particular transformation or that particular application needed and avoid the rest of the data. So it saves the memory and it saves the reading power, basically the computational power as well. That is, there is no predicate pushdown in CSV. There is a limited to weak predicate pushdown in JSON and strong in Parquet. CPU cost high for CSV, very high for JSON, and low for Parquet because the file is compressed and it is faster to read, and the schema is also embedded. So automatically the CPU cost will go down. And production fit, CSV is poor, JSON limited, excellent for Parquet. That's the difference between these 3 file formats. Now we head to the lab. What I'm going to do is I'm going to create a data and write the data in all these 3 formats and read the data back to the Spark from these three formats and show you how these files are read, and I will also show you the difference between the execution time or the reading time between these 3 files, because CSV takes a long time, JSON also takes a long time to read, whereas Parquet won't take much longer to read that file. So I'm going to prove that with a lab. Let's do that. What I'm going to do is I'm going to create a data frame with millions of records and 4 columns. We need this big data frame so we can actually see the time difference between these 3 files, or else that time difference is negligible. So I just want to make sure the data frame is bigger to actually see the distinguish between the time difference. And the advantage in JSON files is, I forgot to mention this point, JSONs are flexible. You can actually store the data in nested format in JSON with no problem at all, while that lacks in CSV. So that is one of the advantage in JSON. It is flexible. You can store any kind of data into it easily. But it is obviously heavy because it is flexible. Now this, like I said, this is just a Python list. There's nothing to do with the Spark about this line, this expression. This is just a Python list of tuples. I'm just creating a data with a list of tuples. I mean a variable named data with a list of tuples, and every tuple, each tuple have 4 values in it. Now I'm going to define the column names and create a list with that column names and then assign to that data frame. That creates a list which is named as columns, which is assigned to the variable name columns. Now we convert that into a Spark data frame. Like that. That will create the Spark data frame. Now we write that to the external location as 3 formats: CSV, JSON, and Parquet. First, I'm going to write that to CSV file. Like I said, I'm not going to explain these write modes because that has a separate topic for that. We'll discuss about these expressions later, but I'm just going to type them in and just execute them. This will okay. Okay, so I typed the code wrong because the location wrong here. You know what? Because I'm not going to explain the write formats now, what I'm going to do is I'm just going to pause the video and resume it after I type in the right codes, right expressions. Now I wrote all the 3 files and named them as employees underscore CSV for CSV and employees underscore JSON for JSON and Parquet for Parquet. And here, these are the 3 files I created. And let me open one of them. There you go. So this is how they are all saved. For CSV, it also saves the header, like I said, along with the columns. Along with the actual data, it also saves the header as a row, and they're all saved in rows format, like that. You see that? So they're all saved in rows. And also, for Parquet, it's almost the same thing. The data is saved in rows, yes. But this doesn't save the header like as in CSV. It doesn't save the header here, so we don't have to define the option and say header is true for JSON. Whereas for Parquet, well, for CSV and JSON, we can just open that file and read the data. Whereas in Parquet, we cannot do that. We cannot do that with a normal notepad or any other tool. Like, I mean, if I try to open this with a notepad, I might see something like this. So we cannot read that file. Okay, now I'm going to read those files back again and show you how they differ in each of the characteristics. We already know how to read a CSV file. We do option and say header is true. And because for CSV the schema is not embedded inside the file itself, we have to define the schema at the time when we read it. So we have to say infer schema here. CSV. And I also want to talk about this thing here. Remember the format to read a file? It has to have the format as one of the configuration, yes, but we haven't defined the format here. You see that? We only defined the options, the two options, one for header and one for infer schema, and then right away we said .csv, and we haven't said .load of and then specified the location of the file. We said .csv of opt and the file location. What we did here is, instead of writing that, we can just write this. Instead of writing two lines, this is equivalent alternative of that same definition. Let me show you. Yep. Let me zoom this in. So this is same as this one. We don't have to say load off and then format off separately. What we can do is we can say dot and the format. If it is CSV, we can say dot CSV off and then define the location of that file. Both works. However you want to define that. I just want to clarify. I just want to give you a clarity about that. So in future, if you saw that and think that's not the right way, but in fact it is. We can write both the ways. Now I'm going to run that. Let me refresh this before. So these are the jobs that are created when I write the files. Now I'm going to read that. This will create another job. Other two jobs and one query. Okay, let's do that for JSON as well. Later we compare the time taken for all of them. Before reading JSON, I'm going to trigger an action for CSV so that we can see how long it takes for to run the transformations on each of those files. So I'm going to run csvdf.select of name. Now to show the difference between the execution times between the files, what I'm doing here is I'm selecting only one column from the given data frame, and then I'm using the count, and then I'm deriving the count action from that. So I'm just selecting one column here, and there you go. It did execute it. Now that create another job. So this is the job that got triggered by the action. I mean, that is the query, not the job, by the way. Now I'm going to read the JSON file. Now this is how I'm going to read the JSON file. This is almost identical to how I read the CSV file, but the only difference is I haven't used that option configuration to define there is a header in the data, because JSON doesn't save the header. We're not going to use that option. Instead, but still, we use the other configurations, the option of infer schema true. So we define the schema with that, and also the format and the location. Run that. Now that is the data frame is created. Now I'm going to run the same operation, same action with this data frame by selecting the name and then triggering that with the action count of. The reason I'm doing that because to show you how column pruning works. Whereas for CSV and JSON, even if I select only one column, even if I'm selecting only one column, which is name, the Spark still reads the whole data frame, all the data that is in that file, because the data is stored in rows. Whereas in Parquet, it only reads that particular column because the data is stored in columns and not rows. Now, the Parquet format. And then right away, we go to the file location. That's it. You see that? This is a lot different. Because Parquet comes with embedded schema, we don't have to define the schema here. No infer schema or no user defined schema. We just right away can just use format. We can just define the format and the location and run it. It reads the file. But there is an error, and the error is, okay, I found the error. Because I copy pasted that location from the CSV expression, I forgot to switch this from CSV to Parquet, and that is the error. I'm going to run that, say copy, paste that, and edit that part as Parquet. Run it. There you go. Now the data frame is created from Parquet. Not created, is defined. Now I'm going to run the same operation. I'm going to copy paste that. Run it. Okay, again. Have to just remove this extra dot. Run it. There you go. Now let's refresh this and see all the queries that got created here. Now I'm going to compare these three queries. The first one, I think the first one is for the CSV. Yeah, scan CSV. The first one is the CSV, and the second one is JSON, scan JSON, and the third query is scan Parquet. If you take a close look at this execution times, the duration of the queries, CSV right here took 6.6 seconds, okay, and JSON took 0.5 seconds, whereas Parquet only took 0.2 seconds, almost what? It almost took less than 40% time to execute the same operation, right? When compared to these two file formats. That is how simple it is. Now we know Parquet is faster than the other two, but there is one more characteristic where JSON, the data, JSON takes a lot of storage. Let me show you. So this query is the JSON one, right? This is the CSV one, and this is Parquet one. What I'm going to do is I'm going to open this job from CSV and see the input size for the records. The same number of records, by the way. It's almost 250,000 per task, 250,000 records per task. It took 9.4 megabytes. Right? Now I'm going to go back and open JSON, the same job for JSON. It took 17.6 megabytes. It took 9.6 megabytes for CSV and 17.6 megabytes for JSON. And now let's compare the same thing with Parquet. It also took 9 kilobytes. Parquet took 9 kilobytes and CSV took 9 megabytes, whereas JSON took 17 megabytes. You see the size difference, right? It is massive. And here we are only using million records, and it only have 4 columns. In real system, or when you work with a company, with a corporate where there are multiple or billions of records with a lot of columns, this difference is massive. Right now, even now, it is a lot different, right? 9 kilobytes and 9 megabytes and 17 megabytes that's a big difference. And that's how these files differ. And that is why Parquet is the best format when you work with big data. It is fast, it is compact, but whereas JSON, it is flexible than CSV. You know, they all have their own upsides and downsides, and it depends on which situation you're using that file format for. For small data, you can still use JSON and CSV. That doesn't make any big difference, but when you're dealing with big data, it's always better to go with the Parquet format. Okay, with that, we're done with this topic. Let's head to the next one. And now in this topic, we're going to talk about schema, inference, and explicit schema. Till now, we just used infer schema, where Spark defines a schema at the read time. Spark defines the column names and the data types while scanning the data at the read time. Whereas what explicit schema is, we define a schema even before we define the read expression, and then we assign this defined schema to that read expression. And it depends in what situation you're going to use which of these. If you want more control of your data over your data, we go with explicit schema by where we define our schema. If you don't, you go with schema inference. There are a lot of downsides with schema inference because Spark does it and we don't control it. And now I'm going to talk about few of those. Let me just open the conceptual diagram first. For that, there it is. So these are the differences between inference and explicit schema. So the major difference here, the major problem with inference schema is, because we are now going to define the schema, how inference schema assigns a data type to a column is, it just takes a subset of that data, just a subset, and checks the data out, reads the data, and then defines the data type from that by just reading that subset of the data. It don't read the whole data, it just reads that subset and defines the schema of it. Defines the data type of it. And the problem with that is, let's say your data that you have, the column has 1, 2, 3, 4, 5, and then it goes to, now what? Let me say 7 random data. Like that, and then 4.4, and then the next one is null. The next one says NA. And you use infer schema, and for this column, what infer schema does is it takes a subset of the data, like I said. Let's say it took this subset of data, okay? And by this subset of data, it defines the data type of that column. And when the Spark read this subset of data, what it thinks? This column is integer, right? Because all the values in that subset are integers, and it just assigns integer data type to it, integer. What happens later is, because our data, that column is not just integer, it is a double type and there are few strings. What happens is, because when we read it, when it reads this value 4.4, which is a double type and not integer type because that's a float, it just converts it to null, so it doesn't read it, and that is how the data get corrupted. We need this type of data, but we don't get it because that will be converted to null. And these two also will be read as null values. NA and everything, null values. That's how it works. And that is one case. And let's say the same column has 1, 5, and say null or not applicable, okay? And it took this subset of data. But that column supposed to get assigned with data type integer, but because it took this subset of data, it reads all the data and it comes to this. If it has multiple data types in it, these two are integer, that's fine. But when it reads this NA and null, it assumes the data is string and it assigns the data type as string. Now what happens is, instead of assigning integer to this column, it assigns string. What happens? Misread. So the data is misread by Spark. And that is why, to have more control over your data and you knew what kind of data you're working with, you can just define the structure and the data types of it and the column names explicitly by yourself manually and then assign that to that particular data. So what happens next is, depending on your configurations, if you assign integer type to that particular column, if that column has integers, the integers will be read. And if you say nulls equal true, what happens is if there is any other data types other than integer coming into that column, it converts that into null because you said nulls equals true. But the major difference here is you have control, right? For the same data from the for the same column that we used for infer schema, if there is a double type after a few records, and we know that column is supposed to be double type, we can just define it with double type. That's how you have more control over it. I will demonstrate the difference between them when I run the lab, but for now, that's how the concept goes. Yeah, scenario, unexpected nulls. We talked about it. Inference, silent. It silently replaces that, fails or null. If we say nulls equals false, that will fail, or that will be assigned with nulls because we have the control there. Type mismatch, we talked about it. Silent cast, error. So if that column has a different type of data, like like the example we talked about, the subset it read has integers and later it adds the double data type, and that will be a mismatch. Corrupted records, partial read, and control failure. Debug timing late because we cannot find those errors that happen because it just converts everything that we need into nulls. If that things it is not supposed to be to be added to that column, it just turned that into nulls. And the only time we find that is when we actually read the data. So the debug timing is late, whereas in this it fails early according to the configuration that we do when we write the schema. Okay, let's head to the lab for this. Okay, let me open command prompt. Now I'm going to write a CSV file and then read it back again. We create obviously a list of tuples. And for the major differentiator, I'm going to use this column, okay? For the first record, I'm going to use integer, and for the second, I'm going to use double, and for the third one, I'm going to use invalid, the string type. So I can show you how infer schema takes that schema as, that column data type as, and how we can define the data type for that column. So now this is a double data type. This is a float. For this, I'm going to say invalid. It's created. Now convert that into Spark data frame. Say ID for the first column name for the second. Salary. Now we got that. Now write that. Do I have the location here? I do. The name. Schema test for that file name. Run it. Now the CSV file is created. Now I'm going to read that with infer schema first and print the schema to show you how the schema is assigned. Name the data frame as df infer. True. And another option for defining the infer schema. True. CSV off and same location. Now I'm reading that same file with infer schema. Run it. Now I'm going to print the schema of it. Infer dot print schema of. There you go. Now you see the schema here. ID is assigned with the actual data type, which is integer, and for all of them nullable is true. So no matter what type that particular column is passed with, that value will be converted to null if that is not you know, an integer for this column. That will be converted to null, and that is how you configure that. And then for name it is string. That's correct. Whereas for salary it is supposed to be double data type, right? For salary it should be double data type, but because it has invalid and it took a subset of data to read, and that subset of data will have this column as well, and that is invalid, and it took that as string instead of double. That is how mismatch happens. And that's how it is. So this all, I mean, we are reading this as so we can see these are integer, this is integer and this is float, but internally they're all considered as strings. Now let's see how can we define the schema and then assign it to that data. For that I'm gonna import something. From that, so we imported StructType to define the structure of the data, and then structure of the field, and integer to define the data types of each column. Now we define the schema first using StructType, so which defines the whole structure of the whole data frame that has struct field. Now for the structure of each field, the first field is going to be ID, is named as ID, the first column. and that should be integer type. And at the end, we can say true or false. If you want to have, if you want your column to have null values, you can say true. Or if you don't want for that column to have null values, let's say when I define this as integer type and the incoming data has something different than integer type, other data types. If I define it as true, that other data types are converted to nulls, so no data will be saved. That field will be left null. But if I define it as false, that will trigger an error, and you will know immediately. But here we're going to use true. And then the same thing. I'm going to copy paste it and change the column name here, which should be name, and type as string, because the second column, the name should be string. And then again copy paste it or paste it. Now I'm going to define the third column, which is salary, and the type should be double type because it does have float values in it. Double type. Close that with a square bracket and a parenthesis. Run it. Now the schema is defined. Now we define the read expression and assign this schema to that. Say df explicit because I'm using explicit schema. Say spark dot read dot option of. Obviously we need to define the header is true. Then schema, here we use the dot schema, here we use the dot schema, and then we name our schema that we created, then the format, and the location. Run it. Now I'm going to print the schema again. Explicit dot print schema of. Now if you take a look at here this schema, the first column obviously that is integer, the second column which is name, that is string, but the third column should be double, and it is double. Nullable equals true. But if we define here as false, this will print for that particular column, the nullable will be false. Now when I run that, this will print the sample data set. Now here we can see the ID, integer, name, string, nothing changes. But whereas for salary, all the types of this data is converted to double, and the types that doesn't match with the data type are converted to null, which is null. Whereas in the other one, we just converted we just assigned the data type as string and kept the invalid as invalid. Here we convert that to a null value, and the integer also to double, and the rest will be the double. That's how explicit schema works. And with that, we're done with this topic. Let's head to the next one. And for the next topic, we're going to talk about StructType and DDL type schema definition. We just talked about schema and inference and explicit schema, yes? And there are types of definition, or there are types of defining the schema when we define the schema explicitly. And the types includes StructType and DDL. And they both have their trade-offs. We're going to talk about that now. StructType is nothing but defining the type in a programmatic way, just like we defined before. And DDL is the modern way where we define the schema in a declarative way, which basically uh, is like writing a SQL query. That's the difference between these two. And I have a table for that created. Yeah, this one. And for each of the aspect, they have their own, characteristics. For type safety, StructType is strong, but DDL is moderate. It is fine, but it is moderate. And for readability, StructType is quite harder to read, but DDL is very easy because it is like writing an SQL query. And IDE stands for Integrated Development Environment, where multiple people from multiple roles work on the same product. In that case, StructType is excellent, whereas DDL is minimal because it is not programmatic way, it is just a declarative way that is not that efficient in that aspect. And when it comes to nested types, there are situations where we declare the type inside a inside a column data type. I will show you in the lab what I exactly mean about nested types. You will understand about that. That in that struct type is excellent, whereas DDL is good. We can still do that, but struct type is the easiest way. External configuration, hard, easy. Production control, struct type is high, DDL schema medium. Well, it is modern way to define the schema. It makes it a lot easier for us to define it, but it is not efficient in the production environment, not efficient enough as struct type in the production environment. It depends on you. It depends on you to which one you choose. Okay, now heading to the lab. Yeah, let's go to the lab. That's it. Let me open the command prompt. Create the list of tuples again. And the nested tuple here in the data. That's it. Now here we created a list of tuples with a nested tuple, nested tuples. Now we convert that into a data frame, a Spark data frame. Run it. Okay. Now what happens is this whole thing is taken as a field in this data frame. You don't care about the data type here. It just takes that as a string. Now let's write that into a JSON file, because JSON is very flexible for these type of nested data, and that's why we're going to save this in JSON format. Run it. Okay, that JSON file is created. Now we define the schema in both types, the struct type and the DDL, the data definition language, both of them. So first, for the struct type, we again have to import those. We want to import this again. We don't need the double type here. We just need struct type, struct field, and integer type and string type. Perfect. We define the first two columns in the regular way that we did before. Just going to copy this again. Paste it here. This is name. This should be string. And then for the next one, I'm going to paste that, but this is location, the third column, and this should be taken out. Use StructType again, and then open that. Now struct field of city string type of and nullable true, and struct field again. Country as string type and nullable is true. Then close that struct type, comma, true, and close the outer struct field. And now close the other struct type again. Like that. Run it. Now that is defined. Well, this is not readable enough because I just wrote everything on a single line. So I'm going to show you what I did there. in this Word document so you'll understand what I did right here. So yeah, we have 3 columns, right? Basically, the first field is ID. The first column is ID, which is of integer type, and the second column is name, which is of string type, and for the third column, which is nested type, and the column name should be location, but it has nested. So what we do is we open another struct type and define the struct field again. For city, we say string type, and for country, we say string type. And close that struct type again, and then comma. This true is for this location field, okay? And we say nullable equals true, and then close that struct field with parentheses and close the whole struct type with square brackets and parentheses. That is what we did. We defined that. Now we're going to use that schema to read the data. And the location is this. Run it. Now print the schema to compare dot print schema of. This will print the schema. That's good. And then actually print the actual sample data. Dot show off. There you go. All right, something went wrong. Now I'm going to debug this and see what happens, because we got null values here and that is not supposed to happen. So I'm going to debug this and be back in a minute, all right? Okay, now I just debugged it and this is the output that I got. I'm going to show you what I changed. What I did is, I haven't changed anything else but the data that we created before. This one, the list of tuples. What I did before is I just created these tuples with the data, and I created nested tuples instead of rows here. So what happens is, when we create a nested tuple and when we read the data with a schema, the data will be read as arrays. The nested tuple, this tuple will be read as array. And when we try to map that array with the struct, it will not match. Because of that mismatch, Spark will just replace those values with nulls because it cannot identify the data type. What I did here is I'm defining the data inside, before I even create the JSON file. At the source itself, I'm defining it as a row, which is equivalent to defining it as a structure. So when I define that as a structure, it is not considered as an array. Instead, it is considered as struct. Now, everything else I did here is identical. I changed nothing. I just copy pasted that and ran the same thing, except for this source data. And everything ran fine. And this is the output that I got. And yep. Now, this is the output that I got for the struct type. Now, let's try with the DDL. Name it DDL schema. Triple quotes. ID int, comma, name as name is string, location, because that is a structure inside the data, I'm going to say struct less than, I mean, that is not less than, that's just acts as a, separator, city, city, say string for that, country, colon, string again, close that, and the triple quotes again, run it. You see, this is how we define the schema using DDL. This is so simple, we can actually read it. So, and that is why I said it is readable. It is nothing but like writing an SQL query. But this is kind of harder. I mean, it's not that hard, but it's kind of harder than this one, right? This is so easy. This is simple. Say DDL print schema. Oh, I spelled it wrong. Oh, I haven't assigned the schema yet. Sorry. So I haven't assigned the schema to the read. So I have to do that first. So df DDL Spark dot read dot schema. Basically, I'm going to use the same read expression which I use for this. So I wrote about this. I'm gonna copy that, paste it here, run it. Now I'm going to print the schema of this one. They both look identical, nothing changes, right? This one and this one, nothing changes. They both look identical. And they both work identical too. There you go. They both work identical, they look identical, but it is simpler and that is complex. But that is good for complex logics, complex structures. When you deal with complex structures, StructType is the way to go. If you want a simple way to define the schema, DDL is the way to go. And that's it. With that, we're done with this topic. Let's head to the next topic. We're done with the data ingestion phase, and now we are in data frame transformation phase. And the first topic in this is narrow versus wide transformations. I'm going to cut the difference between these two in just one line. Basically, a narrow transformation is a transformation that can be done without any shuffle or without any data movement between the partitions, whereas the wide transformation requires data movement between partitions. And the reason this is a big topic is depending on the data movement, we can actually see which transformation uses how much of compute. Whereas where wide transformations have multiple, data exchanges between the partitions, the shuffle, that cost network usage and pressure on the memory because it uses network input and output between the partitions, and the shuffle happens because of that, the memory might be pressurized and the network usage is high, which might increase the cost of execution. When you work on a Databricks environment or something like that, it depends on how much memory and how much computation you use, right? And that might increase the execution cost when you run wide transformation when compared to narrow transformation. That costs you more in terms of network usage and the memory and the CPU power too. And these are the narrow transformations. They basically have one input partition and one output partition and nothing else. Select, filter, with column, drop, map, union. And wide transformations include group by, aggregation, distinct, join, order by, repartition. In these transformations, it is mandatory to distribute the data and then to execute shuffle between the partitions. And that is why these are wide transformation, those are narrow transformations. Now I'm going to demonstrate that with a lab example. For that, I'm going to create a data frame. I, I modulo 5. Then convert that into a Spark data frame. Like that. Now first I'm going to write a small narrow transformation and show you how that works in the backend. What we did here is we are filtering the data frame with the group column to only have anything greater than 2 and select the ID column from that grouped data. And because I am only using filter and select, which are part of narrow transformations, see that filter and select, they both are part of narrow transformations. It only creates, it doesn't require any shuffles. No. And then run this action basically. Now before running that, I'm going to show there are no jobs in this one, the Spark UI. I'm going to run this. And now let's open the Spark UI. Refresh. You see that? Because that just include narrow transformations, it only creates one partition, one job. And when I open this stage, it only has one tasks. And because tasks are equal to partitions, this is only done in one single partition and there is no distribution between the partitions happen here. This is how narrow transformation works. Now let's run a wide transformation to see the difference. So we can just distinguish between narrow and wide. So for wide, what I'm going to do is I'm going to use groupBy because groupBy is part of a wide transformation. And I'm going to group the data using group column and aggregation factor as count. Run it. Oh, my bad. And run df underscore white dot show off. Run it. That is executed, but this requires partition and shuffles, which means you will see multiple jobs. You see that? It created 2 jobs and also multiple tasks which represent multiple partitions. There you go. The data is partitioned into 4 different parts. So 4 equal and separate parts. And then grouped together and then shuffled and aggregated. There is a global aggregation happened after. So what happened is, first the data is separated and distributed among the partitions. There are 4 partitions, and then for all the 4 partitions the group by got executed. And because there are only 5 variants in group column, so it will create 5 unique rows, only 5 records when we group it. And we aggregated the other column as count, right? This one as count, and we grouped it with 5. Grouped it with group column. And that is why what happens is, for all these separate partitions, the group by will execute separately for every partition. And for every partition, we have 5 records now. Then what happens is, all these 5 records from all 4 partitions will be combined together in one partition later, and then the group by will be executed again, which combines these 20 records that are split among the partitions to one, and it results one unified 5 records, which is the result, this one. We can actually see that clearly when we open the query here, SQL data frame, open the query, and here we can see the physical plan. And here you see scan existing RDD, hash aggregate, separate hash aggregate, and then exchange between the partition happened here, and the shuffle happened, and then aggregated again. That is global aggregation at the other one, right here. That this is one stage, and this is the other stage. So 2 stages created, which are divided by shuffle boundaries. Whereas the other query, which is a narrow transformation, doesn't have any shuffles and only happened in one single stage. That's the difference between a narrow transformation and a wide transformation. What we get, the output we get doesn't change, but the internals of Spark does change. This has to be recognized. With that, we're done with this topic. Let's head to the next topic. Now, our next topic is basic transformations. Well, 90% of the application or PySpark transformations are basic transformations, and the rest will be intermediate and advanced transformations, but 80% of them are basic transformations. And knowing what these transformations do can improve the performance of Spark and also save some money for you when you work with big data. And I'm going to demonstrate you how that will save money. And to demonstrate that, I'm going to use these most commonly used basic transformations, which includes select, filter, and with column. And let's see what each of their operations do. For select, it chooses a subset of columns. So it basically picks the columns that you only need and ignores the rest of the columns. So that will help Spark and you to save money, and help Spark to only read the columns that you want. And there is this filter. Filter removes the rows based on the condition that you define. So it filters the rows, whereas select basically filters the columns. And there is with column. With column creates or replaces a column and applies an expression that you define for every single row. And remember these operations that are done by these transformations. Okay, later we will talk about those. Now, my point. I know Spark uses Catalyst Optimizer to optimize the physical plan from which is derived from the logical plan by ordering these, but it is not that smart enough where it can actually change the flow that you define. Okay, so Catalyst does its job to optimize the plan, but you have to it's in your hand to optimize the logical plan. And how we can do is, when we write the expressions, we have to take care of the order that we write the expressions in. You don't just think of it like, okay, I want these transformations and I just go and type the expressions for that transformations, and then you don't care the order. If you don't care the order, you might be end up spending much more money where it doesn't need that much on the computation. So I'm going to demonstrate that with an example. Okay. First, let me show you the example. Let's say you have this data frame. Yeah. And this data frame has 3 columns. Let's name this ID. This one as product. And this one as price. Now, if you want to create a column or replace or create a column which shows the final price after adding, let's say, tax to it. Okay, you know what, let me also add one more column here. Let's say you all also have description. Now your result table or data frame should only have, you want that result data frame to only have 4 columns, which includes ID, product, and price, and the final price. And you don't want description there because you just want to add that column and remove the description because you don't need it. And also you also have another condition. You only want to have want the data in that final data frame of the products that has the actual price that is greater than, say, $300. You don't want any products that are less than $300. In that case, to actually do that, instead of if you run that condition first, let's say if you run the with column condition first and say with column and define the condition to multiply with the tax, add the tax to it, say price plus tax. You write this condition. If you write this expression first in your application, in your Spark application, what this does, this will calculate that uh, that price plus tax for every single row, right? An expression calculate is applied to every single row. So even for the rows that you don't want in the output, which includes the products that are less than 300, will also get computed with that expression, right? And what is that? That is just waste of your computational power, right? And it takes more time as well. So what if we filter those out first, filter those rows out first of the products which have the price less than 300, and then apply this? What happens? You filter that out because you will filter that out later, but if you filter that out before you do this expression, you are saving some computational power, right? And the same thing, if you remove this column before you do anything, Spark doesn't even need to read this column anymore in that part of that data frame, right? If you just say select, if you just use select first, so if you just use select first and filter this column out, and then you use filter next and filter out the rows that you don't need, and then apply this expression to the data frame, you will save a ton of computational power and money, right? And that's practical. And that is why writing your computations or writing your transformations in a flow that actually saves you something is important. Not just blindly writing the transformations and expecting, I mean, you will get the same output, but expecting a good performance doesn't make sense. That's how Spark works. Now let's head to the conceptual diagram. Well, it basically says the same thing. The source data, select column reduction, filter row reduction, and then we apply with column, which is computation. Because we do these two filters at the beginning, the computation is reduced and you save something, right? You save time and computational power, which means money. That's how it works. Now let's head to the lab. For the lab, I'm going to create a data. You know what? I'm going to also add something else here. Say I plus 1, enter. Oh, I spelled for wrong. Should be O. Run. Convert that to Spark data frame. Run that. That will create the data frame. Now I'm going to write the transformation. UDF transformed equals UDF dot select So here I'm just filtering out the columns. I'm just selecting these two columns and excluding this column, which is extra. It's because I don't need it. So I'm going to do that at the beginning. And after that, I'm going to filter out the rows that are, let's say, greater than 5. And then now I'm going to execute the computation with column and another transformation that creates another column and say group plus 1. Close the parenthesis and run this. We did got an error. Name call is not defined. So we have to import call first to use that call. So from run it. Now copy paste this. Run it. That will run. Now what I did here is I first filtered out the columns using select. So I excluded that extra column out. And then I filtered out the rows using column of group that is greater than 5. So only the rows that has the value for group as that is greater than 5 will be moving forward and the rest will be left behind. And then the two transformations create two extra columns basically. And with column group double, call of group times 2. It just multiplies the group times 2. And then the other one with column, another column. So I'm going to create two new columns for the result data frame. And the second column will be group plus 1, call of group plus 1. So it just adds 1 to it. So you see the flow here, right? First I filtered out columns and then rows, and then I ran the transformations. If we do this other way around, we can still do that. We can add the columns first and then we can do the transformations first and then do the filters next. But that takes a lot of computation compared to this one. So that is what we have to remember when we write a transformation. Go for the optimal way and not make things complex. Run it. I got the output. I will get the output if I do that transformations or do that expressions or write the expression on the other way, I mean in the other way, but still it is not about changing the output, it is about changing the way the computation works here. So we're done with that. Let's head to the next topic. And our next topic is actions and triggers. I actually talked about this topic along the way already, so I don't think I need to talk about it anymore. But I want to create this topic so it has everything that everyone needs to know. But I already talked about it a ton of times since the beginning. So I'm just going to go give you a quick overview of what it is again, and we'll skip to the next topic. So the actions and triggers. We know action are the one that triggers the execution, and until then the transformations will not get executed. They're just the logical plans that gets created because of lazy evaluation. Only when an action gets executed, that is the only time when the Spark is triggered and creates the jobs, and they are called trigger points. And the most commonly used actions includes count of, show off, collect of, take off, and first off, and write off for each of. From this, we used show off and count off. We haven't used any of them. Count off counts the rows. We know that. We got the output as well when we ran that. And show off displays sample rows. We already talked about it. I ran it. It returns the sample rows from that data frame. And collect off brings all the data to the driver. Take off and retrieves first n rows. First off returns first row. Write off presses the data. For each executes side effects. So they all have their own functionalities. And when you run these actions, you have to remember collect off pulls entire dataset to driver memory, which means the driver, there is a high chance of for the driver memory to be, overfilled with that memory, because everything is pulled to the driver memory and that might get filled. So you have to be careful when you use it. If you have a lot of data and a small driver memory, it is not a good choice to use collect off. It crashes. There is a high chance to crash the driver if you run that. And show off triggers every execution from the beginning to the end. We already know that. And yeah, that's it. And we have a conceptual diagram, basically the same thing that says we write the transformations, and our transformations are nothing but logical plan that will not be converted to physical plan until and unless we trigger an action, and that is when it will be converted to physical plan by catalyst optimizer, and then it moves on from that. To be more precise of what happens in the backend, I already wrote what happens. I'm gonna read it out for you because I keep forgetting. So when we write a Spark code and run it, it creates a logical plan. We know that, right? And when I or the user trigger an action, that is when Catalyst Optimizer optimizes a logical plan and produces a physical plan. And then Spark DAG scheduler. There is a DAG scheduler which breaks that physical plan into stages. We know about stages, yes? The stages which are separated by shuffle boundaries. So DAG scheduler breaks that physical plan into stages based on shuffle boundaries, and task scheduler creates a task and run them on executor. This is how the internal flow goes. Okay, with that, we're done with this topic as well. This topic is pretty small because we already talked about it since the beginning. Let's head to the next topic. We now entered into the phase 5, which is intermediate transformations and shuffles. And the first topic we're going to talk about is group by, aggregation, and distinct. These are all wide transformations, right? We talked about them. These are all comes under wide transformations. And because they have shuffles and all of these uh, transformations need the redistribution of data among the partition, which basically means shuffles, and that is why they come under wide transformations. We already talked about it, but we're going to go deeper into that. Each one of them needs to go on through this process, redistribute the data across partitions. So basically, when we run an action, the data will be distributed among the partitions, yes? And if you want to run group by among with that data, you cannot just run group by globally when the data is partitioned, because all the partitions run separately. So you cannot group by globally. What we can do is we group by separately for every partition first, and then we bring the related keys together into one partition, and then we perform the group by. We don't perform it, we just write the Spark expression and Spark does it for us. But this is the flow it follows. And same for aggregation. Aggregation includes the arithmetic operations and stuff like that. The same thing. It is happen for every partition separately, and then uh, bring the related keys together to one partition, and happens the same thing happens globally later. And same for the distinct. Distinct is nothing but picking the deduplicating, picking only the what to say, basically filtering out duplicates and only picking one of those duplicates and removing the rest. So the deduplication as well. We cannot deduplicate when the data is splitted among all the partitions, yes? What we can do is deduplicate, separate in partitions and combine them together and in one partition, and then deduplicate again globally. That's how that works. And these are group by look like. We already used it, so it doesn't need any special interaction for this. We just group by this column, and we use aggregation dot count of at the end to to aggregate the other column. And these are the aggregations, the common aggregations which we use. Count, sum, we already used count, we never use sum, but it is nothing but adding them. And then average of that, max of the given values, and min for minimum of the given values. They all require moving data between partitions and shuffles. Distinct. It looks something like this: df.select of user id dot distinct of, it just deduplicates that particular column. And yes, does it have? So it does have a conceptual diagram, which includes the pre-shuffle stage. The data is shuffled, the data is partitioned randomly without carrying anything. And then in the shuffle phase is where we shuffle the data between the partitions, and all the related data will be assembled in one particular partition like this. And then we run these, then we get the aggregation or these wide transformational outputs. And this is a representation of that in a conceptual diagram. Now, I think it's time to head to the lab. Well, it doesn't have lab because we already used group by multiple times, so it doesn't need any separate explanation, right? And the distinct and aggregations. We used groupBy, and we also used aggregations when we used groupBy, because count of is basically aggregation, and distinct is almost the same. But I showed you the example, right? How the distinct can be written as like this. If we pick the column and we say distinct of, that deduplicates that column, and after that, that column will not have any duplicates. So this topic doesn't need any lab for this. So let's head to the next one. Now for our next topic, we're going to talk about joins in Spark. There's not, you might think there's nothing special here, but there is. Especially for this distributed processing tool, Spark, there are two types of joins: shuffle join and there is broadcast join. And the difference between these two is massive. And there are situations where we can use broadcast join, because broadcast is the best way to go when you do a join that takes less computation and input output, network complexity, low network complexity, whereas shuffle join is high network complexity and more computation power. But there are a few cases where you cannot use broadcast join. Now I'm going to explain how these two joins work with the conceptual diagram. So let's head to that. Okay, we're here. So this side is shuffle join and this side is broadcast join. First, talking about shuffle join. When we write a join transformation in Spark, where we join two data frames, so this is the flow, okay? So let's say we have two executors, okay, and the data frames, the two data frames will be splitted among these two executors equally. And when we run shuffle join, this is the initial state. After, when we run shuffle join, after this initial stage, the shuffle phase happens, where we shuffle the data in the data frames between these two executors in order to get the result for the join, because we cannot just join two data frames which we only have partial data, right? And so because we have partial data here in this executor for the two data frames, and the the rest of the data in the other executor, we have to shuffle, and after the shuffle we can get the output data frame, which is df3, after join, the output data frame. This is what shuffle phase looks like. This increases the network complexity and increases the computational complexity too. And whereas on the other hand, we have broadcast join. This is quite different than shuffle join. What happens in broadcast join is, instead of splitting the data in these two data frames among the executors, what happens is, if one of these two data frames is relatively smaller and can be stored in the driver memory, what happens is this small data frame will be broadcasted to all the executors through the driver, and only the data of the other data frame, the larger data frame, will be split across the executors. You understand that, right? So it goes like this. This is the representation and this is the driver, and the driver broadcasts this data frame 1, and this is the initial stage. Says broadcasted by driver. This data frame is broadcasted by driver to all the executors. Now instead of going for the shuffle, we don't need shuffle here. What we can do is, we can just broadcast that and do the join separately in these two executors and get the output, get the final data frame out as the output. That's how it works. Now I think you got the concept here, right? The difference between the shuffle join and broadcast join. But you cannot, I know broadcast join is more efficient than shuffle join. you might also be thinking that in the same way, but there is one flaw in broadcast join, and that is you cannot use broadcast join if both the data frames are big or massive, because it depends on the driver memory. You cannot just broadcast a data frame. You can only pick a data frame which is so small and can be broadcast easily. That is the flaw in broadcast join. So in only a few situations you can use broadcast join, but if you can, go for it. Or else we have to use shuffle join, which is complex, relatively complex than broadcast join. Now heading to the lab here for the joins. Out of the lab, first I'm going to create the large data set. Say orders equals. Okay, now convert that into a data frame. And it with that parenthesis. So now I created this data frame, which will be our large data frame, which has 3 columns. And yeah, the 3 columns are order ID, customer ID, and amount. I think I spelled it wrong, so I'm going to create another data frame. Say that. Run it. Okay, now I ran that again by fixing that spelling. Now I'm going to create the smaller data set, which will be customers. This is orders and that will be customers. So now I created a data frame for customers, which is a shorter data frame comparatively, which has only 1,000 records. And the first column will be customer ID, which goes from 1 to $9.99, and the other one is customer name, which will be customer underscore I, which means that will also range from 1 to 1000. Now I'm going to run shuffle join and broadcast join for these two data frames, and I'll show you the internal difference that Spark makes behind the scenes. So if df join underscore shuffle, that is a transformation. These are regular join, by the way, which is shuffle join, where we say this is the left data frame and this is the right data frame. We are just joining them with this as the joining parameter, this column as the joining parameter, the customer ID. Run that. df underscore join shuffle. Now I'm going to run the action. Run it. We got the output with the join result. Now I'm going to do the same thing with broadcast join. For that, I have to import broadcast. Right. Now do the broadcast join. df underscore customers, comma, customer ID, and close the parenthesis. Run it. Okay, what is that? df underscore customer is not defined. Is it? Oh, it should be customers. Okay. I forgot to put an S at the end. Should be plural, not singular. Run it. Perfect. Now df underscore join broadcast dot show off. Run that. So the output for both of them will be the same, basically. But now let me refresh this. Oh, I think these are the two. Are they? Yeah, I think so. So this is the first join, which is shuffle join, which created 4 jobs. Let me open that. Filter, exchange, shuffle. Okay. To actually compare these two joins, what I'm going to do is I'm going to open the same web page, same Spark UI on a different tab so you can see the difference between these two. Okay, that. Now, let's compare the whole query and compare the duration that took for both of these joins. Firstly, this is our shuffle join, yes? for our shuffle join, it took 0.8 seconds to execute, and it created 4 jobs in order to get the output. Whereas the broadcast join only took 0.3 seconds and it only created 2 jobs. See that? Now that's one of the difference. It took less time comparatively to the shuffle join. Now let's open shuffle join on this tab, the physical plan of shuffle join on this tab, and on the other tab, on this one, I am going to open the other one. Can I do that? Oh yeah, I can. Nope. This one. Now you see the difference between the physical plans here. This is a shuffle join, and this is the this is the broadcast join. If you take a look at the broadcast join, there are no shuffles happen at all. You see that? So it scans RDT, this one in this stage, and filters out broadcast hash join. So it broadcasts and joins with the broadcaster table, and then project, collect, and adapt to Spark plan. Whereas on the shuffle join, this is the flow for it. You see how massive it is? And it also has shuffles in between. And that's the difference. A shuffle join is a wide transformation, whereas the broadcast join is a narrow transformation, kind of narrow transformation. So if you had a chance when you run a join, go for a broadcast join. If you don't have any other way, you have to go for the regular join instead. But yeah, it depends on your situation. If you have at least one of the table is shorter and can be broadcasted by the driver, go for the broadcast join. Now I think you got it. You got the idea clearly. And that's the difference. I'm going to close this, make this bigger. Jobs. Okay. With that, we're done with this topic. Let's head to the next one. Now talking about our next topic, which is partitioning, repartitioning, and coalesce. We know what is partitioning is, yes? Distributing the data to multiple executors. And what repartition is, once this partition has happened, we can configure the partition by running repartition. So we can repartition the data again according to our needs, and we can configure that as well. And what coalesce is, it reduces a partition without the full shuffle. And there is something we have to know about that. So if you think any of the partition has more data, let's say the partitions have skews. Skews is nothing but one partition having more data and the other partition having comparatively less data. The other partitions having comparatively less data and one partition having more data, which means that particular executor which runs or executes something on this partition takes longer than the other executors, and that is what a skew means. Because of that delay, the output will also be delayed because everything has to wait until this partition executes that big skew. That is what a skew is. Imbalances in partition, basically. If you repartition the data, the balances will be, the skews will be taken out and balance will be uniform all over the partition. So they basically have close to balanced data, close to balanced, not fully balanced. We cannot guarantee a fully balanced one, but a close to balanced one. There might be a one or two records going up or going down, but not a big skew. Whereas in coalesce, it only focuses on reducing the partitions, and it doesn't care about the skews. Let's say if you have 4 partitions, okay, and each partition have 250,000 records in each of them, okay, and when you want to collapse the partition and, say you only want 3 partitions from that, what happens is uh, in order to collapse these partitions, these 4 partitions into 3, 2 partitions will have one set of data, I mean equal data, and one of that partition will have a skew because it just collapses those partitions together in that it doesn't do a full shuffle, which means it doesn't care about skews. And we already know about this definitions. What are the responsibilities of partitions, right? Partitions determine how many tasks to run because every partition will be assigned to one single task, right? So that's how every, and that is how it defines how many tasks going to run. Then we have repartition, forces full shuffle, so it forces full shuffle and redistribute the data evenly. But whereas in coalesce, it doesn't redistribute the data, it just collapses the partitions together and it doesn't care about the skews at all. Repartition, by the way, it not just increase the partitions, it can increase the partition or it can also decrease the partition too. No, so this is how we do it. So let's say we have df is our data frame, and it is partitioned like 60. So it is partitioned to 60 partitions, and you only want 50 partitions. What we can do is we say df.repartition of 50. What happens is it'll be full shuffled among the partitions and will be redistributed among 50 partitions alone, not 60. And they are all distributed evenly without any skews. Whereas in coalesce, it merges partitions, avoid full shuffle. It doesn't go through the full shuffle. And as a result of that, what happens is it only merges partitions, yes. And like as in the example we talked about, when we have 4 partitions and we need 3 partitions, what happens is it merges 2 partitions together, which might in result have 500,000 records for that partition alone, and the other 2 partitions have 250,000 records. And that is how coalesce works. See, leaves distribution uneven, cheap operation. But it is cheap than repartitioning because repartitioning asks for a full shuffle. Obviously, shuffling means creating a new stage. Creating a new stage is nothing but increasing the cost because that is relatively expensive than coalesce, whereas coalesce is cheap. But coalesce is only used to collapse go down in partition, whereas repartition is used to go up or go down in partitions. The behavior of these two is compared with this: aspect and repartition coalesce. Repartition and coalesce. So first, shuffle. Repartition does shuffle. Coalesce, no, by default. Increases partition? Yes, it can. Coalesce? No, it cannot. Decrease partitions? Yes, repartition can decrease partitions, whereas coalesce also can decrease, but it cannot increase. Data balance? It balances the data evenly, whereas coalesce potentially skewed. The output data can potentially be skewed, and the cost is higher for repartition because it goes through the full shuffle, whereas coalesce is cheaper because it doesn't deal with the shuffles at all. It doesn't care about skews and doesn't deal with shuffles. Now, I think now you got the idea of to distinguish between these two, repartition and coalesce, right? Now let's head to the lab. Let's have a demonstration. Now for the lab, I'm going to use the PowerShell again and run, create a data frame and show you the difference. And copy paste this and save 25. Copy paste this whole thing again and again and again. And I'm going to change this to 4, this to 3, no, this to 3, this to 2, this to 1. Now I'm trying to create a data frame that has a skew. I mean, not a skew. So one key has huge data compared to the rest of the keys. So here for the key 0, I'm assigning 90,000 records, whereas for the other keys 1, 2, 3, 4, I'm just assigning 25,000 records just to get that skew. Run that. It should be end with a closed parenthesis. Okay. Say, create the data frame out of that data. Now this will show us by default how many partitions are planned in the logical plan for this data. When I run that, it says now it is already planned to partition the data into 4 equal parts, 4 equal partitions. Now if I run df repart equals df dot repartition of 5 to repartition the data into 5 equal partitions, and then run df repart dot rdd dot get number of partitions, and that says 5 partitions. So now we repartition the data which is already partitioned into 4 partitions to 5 partitions using repartition. And when I run df repart dot count of, this will trigger an action. Now let's head to the Spark UI, refresh it. There's the job. I'm gonna go here. There you go. Now if I haven't repartitioned the data into 5, see that? So basically what happened is, by default Spark partition the data between the partitions, yes. So by default, it partitioned into 4 equal partitions, and this is the job for that. So it partitioned into 4 equal partitions with 47,000 records on one, 48,000, 47, 47,664. So it is partitioned into 4 partitions. Now, when I repartition that into 5, so it reshuffles. So it asks for a full reshuffle, and then it is partitioned again into 5 equal partitions. I mean, close to equal partitions. Like I said, it can go 2 records up or 2 records down, but it is close to repartition. See, 38,001, 38,001, 37,999, which is 2 records down, and 37,998 for this one, which is 3 records down. So it ensures close to equality. I mean, close to what to say, uniformity. Whereas here, by default, when Spark distributed the partitions, they are not even. If you take a look at this, you see this? The first task got 47,100 and the second task got 48,100, which almost have 1,000 records of gap. And because of that, this duration differs between those two, right? This is executed in 69 milliseconds and this one takes 71 milliseconds. So there is a skew. Well, for million data, for millions of records and just couple of columns, that duration gap is so small. But when we work with big data, like I said, the duration will be so massive. And here, and on the other hand, here, every single task is almost equally, I mean, executed in equal times, right? Because all the records are distributed equally across the partitions and there are no skews. There are no potential skews. Now, let's run that with coalesce. I'm going to use the same thing and say df repart equals dot coalesce of 10. Should I say 10 or no, it collapses the partition, so let's say 3 or let's say 4. Run that. rtd dot get partitions of. So I coalesced the partitions to 4 back to 4 again. I repartition to 5 and again coalesce that back to 4 again. Now I do df coalesced dot count of, run it. I got the output. I get the same output, but the point is the repartitions, right? Refresh that. Extend the completed jobs. Here, now it is executed in 4 jobs Open that, and there you go. Now you can actually see the skew here, right? We distributed the data evenly using repartition to 5 tasks, and we coalesced to 4 back again. And coalesce, like I said, will not go through the full shuffle, and it doesn't care about the skews. And because of that, what happened is, for the first task, it assigned what, 115,000 records, whereas the other 3 tasks only have 25,000 records. You see the difference between the volumes, right? And that will cause a lot of skew. I mean, lot of, what to say, time difference between them, because this task alone is of size 11.8 kilobytes, and whereas the other ones are just 2.6 kilobytes. These are what the demerits of coalesce. And now I think you got the idea here, right? That's the difference between partition, repartition, and coalesce. Now let's head to the next topic. And now moving on to our next phase, which is phase 6, advanced functions. And our first topic will be window functions. Yeah, we have window functions in Spark as well, like we have window functions on the other tools like Python or SQL. We do have window functions here as well. If you don't know about window function, if you haven't heard about window function yet, for you, I'm going to explain what window function is. Window function is nothing but performing a calculation across a set of rows without actually collapsing the data like we do in groupBy. So, it's nothing but implementing calculations on the data, but without collapsing the rows. Whereas in groupBy, we collapse a set of related rows, or a set of rows by a particular column value, and then aggregate that to get the result, which we collapse it. But whereas in window functions, we can use the same we can do the same process without collapsing the rows. Well, we still get the same functionality of computing, or I mean running the operations, but we don't collapse any rows. To be particular, let me show you some examples where we use window functions. We use window functions for ranking, to rank each row or each record, and running totals. Running totals are not normal totals. Normal totals, we sum all the rows or set of rows, right? But running totals are different. What they do is they sums up the values while we go down to the rows, and starting from the first row, it adds that first row and the second row value, and gives the total for that particular row, and then it adds that total to the next row and gives that particular total. So that is what running total means. And also moving averages, same like running totals, these are moving averages. Moving averages takes average for the first two rows and assigns to the second row, and for the third row, it takes average for the first 3 rows and gives the value of that average to the third column. So, and that is what moving averages. And also lag and lead. Lag shows the value of the previous record, and the lead shows the value of the future record. That is a few of those functions, the window functions that we can use. And this is how a basic window function looks like. It has like 3 components. One is we partition the data using window.partitionBy. So we partition the data by user ID. This is something like groupBy, but we're not going to collapse it. Instead, we just partition that set of data for the user for the common user ID, and then we order just for that partitioned user IDs separately for that user IDs. So we order by event time. So we change the order for that particular um, user ID alone. That is how it works. And then frame definition row range. And then comes the frame definition. Then we use this window function on any of the column when we use the transformation. I mean, to create a column using with column. So we use that window function like that. Okay, here what we did here is we just partitioned by user ID and ordered by event limit. So they get into order from ascending to descending. And then using this window function, we create a new column by using df.with column and the column name as rn and the row number, and we just number the rows because we already ordered them. When we number them, we say we go from the lowest to the highest, so we go in the order. So that's why we use row number over window spec. We're not just going to blindly number all the rows, we number them by the partition because that is a window function that we defined. That is how window functions work. That is how normal window function work. But when we run that in PySpark, well, like I said, it won't physically collapse a table, but still for Spark to actually run that window function, it does need to shuffle the data among the partitions because it needs to partition the related data together to get that output, right? And that's why Spark does have to physically shuffle the data to actually run that. Yeah, that's the main point here. And here, let's do a simple lab to see how window functions work. Now I'm going to open command prompt. Now I'm going to create the data first, obviously. Okay. Now, I think you got what I'm trying to do, right? I'm just trying to create a data frame with 3 columns. The first one will be the user, and the second one will be the date, and the third one is amount. And I'm going to partition by the user ID and order by the date, and then I'm going to create a new column from that. That is what I'm trying to do, and that is why I created this data frame. Now I'm going to define the window. For that, I have to import something. I'm going to import the window, and I also want to import row number. Like that. Now, I'm going to create a window specification and name it window spec equals use window, the module that I imported, window dot partition by the user. Now, after partitioning by user, let's say instead of date, let's say order by amount. Okay. Now, for this window specification, we partition by users. So we partitioned, so which separates user A from user B. The records that have user A from records that have user B. Now, after that, I'm ordering the rows, all the records by amount. For A group separately, the A partition separately, and the B user partition separately for that order by. Okay. Now I'm going to create a new column and say rank, comma, row number. Now, what row number function does is it just assigns a row number starting from 1 to infinity. And because I ordered that using the window function, now only the ranks are unique in that particular partition. So the ranks are unique only for A user, and the ranks are unique for only B user. They're separate. So there will be one record will be on the rank 1 on user B, and there can be another record with the same rank on user ID B because they are both partitioned. Dot over window spec. So now I define that expression. Now I say, now I call the action. This will create the job. Right now we only have 2 queries. Run that. You see what happened here, right? So it partitioned by user, A user separately, So it partitioned by A user separately and B user separately. And for every partition, oh, and the rank is global, by the way. Okay, so the row number is global, but the order along the partitions are separate. But the row number is global because the row number is outside the window. And that's why A is yeah, A alone is ordered and B alone is ordered, and the ranks are global, but the order. Wait, what did I do? Oh, I just found the error that I committed here. The error is at the window spec. When I define the window spec, I partitioned by user, but the actual column name for that column in that data frame is users, plural and not singular. So I have to run from this line again with the right spelling and run from here again. Run that and run this one again. Let me refresh the queries. Okay, this query is not valid. So run this again. Oh, my bad. And run that action again. Now this makes sense. Now, because we partitioned by the users, user A and user B will be partitioned. They are not grouped together. The rows will not be collapsed, but they are partitioned virtually. See, they are partitioned and ordered depending on the amount. So the amount goes from ascending to ascending order, which means lower amount to higher amount, and then will be assigned with the rank, which is the row number starting from 1 to 1, 2, and 3. And this will refresh for the next partition. For partition with user B, the row number refreshes and starts from 1 again and 2. That is how partitions work, partition by work, and that is how window functions work. Now let me just refresh this. And there is the fiscal plan. You see, the shuffle happens. And here's the window. Yep. Though the partition or the grouping is virtual, the shuffle still happens in window functions. That is what my point to prove, and also to demonstrate how window functions work. Okay, with that, we're done with this topic as well. Let's head to the next. Now, our next topic is handling skews. We already know what a skew is. A skew is nothing but a large chunk of data getting assigned to one partition when compared to the other partition, which has relatively less data than that skewed partition. Well, there are a few ways to handle skewed data. If you actually find a situation where there is a few skewed data, what you can do is there are a few methods to deal with that, which includes salting the key. What salting basically means is we just create variants of that huge that key. We just create a variants of that particular key which has huge data uh, and split that key to multiple other variant keys. So the partitions, when it is partitioned, that the partitions will be balanced together. Well, you basically won't be facing this you normally won't face this. Even if a key has that huge chunk of data assigned to that key, still the Spark optimizer partitions the data, so every task or every partition is partitioned with the same or close to identical number of rows. But just in case, if you find yourself in this situation, these are the strategies that you can use to fix that skew. Salting the key, creating multiple variants of one particular key and fixing that skew. And there is broadcast join. We already talked about broadcast join, which takes care of that, and then filtering before aggregation. So we just filter that key out, the key that has huge number of values assigned to that particular one. So we just filter that thing out and go work with the other keys. We can do that, or we can just do salting if we don't want to lose the data for that skewed key. We can use salting. And to be precise, I'm going to run this example. Instead of writing the code, I'm just going to copy paste this and show you how it actually works. Okay. I think I just copy paste one line at a time. So I created an empty list with the variable name data. That is a Python list. We're not entering Spark yet. From here, I'm going to run that and paste this line with indentation as 2 spaces or 4 spaces. Run it and run it again to close the loop. Again, run it. And the indentation has 4 spaces, 1, 2, 3, 4. Paste it, run it, and hit enter again to close the loop. Wait, it needs another parenthesis, right? Yeah. Close parenthesis and hit run again to close the loop. And create a data frame out of it. In the close parenthesis, run it. Perfect. Now what I did is I created a data frame with only 2 variants in the key, which is hotkey and the other one is key and the number. For hotkey, just one single key. I'm assigning 1 million records, whereas the other key, which changes according to the range, the I, it only has one value for every key, whereas the hotkey has million values assigned to it. No, not million, 100,000 values assigned to it. So that's a big skew. Usually, Spark will handle that, but just in case if Spark doesn't handle that, then we can use salting. Okay, let me run this transformation. Run that. This executes. You see that? Only this key has 100,000 and the rest of the keys only have one record per key. So let's go to the UI, open it, click on that, click on that. It did create a skew. You see that? So yeah, it did create a skew. One task has a lot of data compared to the other tasks. It did create a skew. Yeah. This one. So only for this task, the data assigned, I mean, the data that is wrote is this, but the data assigned will be even more. Even the data written is 20 kilobytes, whereas the other records only wrote 73. There is a skew. So let's see if we can fix it by solving. What I'm going to do is I'm going to import a few things first. And create a new data frame out of the old data frame. Oh, forgot to end the double quotes. Double quotes, run it. Now what I'm doing here is I'm just creating a new column saying salted key and using concat. Concat nothing but combines everything together, and I'm combining df.key, which is this hard key with literal underscore, nothing but just an underscore. So I'm going to combine the key with the underscore and random times 10. So what randoff does is it generates a random decimal number between 0 to 1. It can be 0, 0.1, 0.2, 0.3, 0.5, 0.6, 0.7, and it will be then multiplied with 10, which becomes 1 to 10. And that will be combined after the underscore will be assigned to the new column salted key. And then we do count off and show off at the same time. So we're going to group by the salted key. Okay, that is good. Now show off. Okay. Now you see what happened, right? Before when we run it, it only has this hotkey has 100,000 records assigned to it, whereas now that hotkey is separated to multiple segments, basically the multiple variants of one single key. We used concat to add underscore and a random integer for every key. So that is how we salted that key, and not just that key for every key, but we only have one key here with multiple values, and that's why only hotkey got salted and the rest of the keys basically remained the same, but a random a random tail got added to every key as well. But the output is basically same. Let's go to this, refresh. Now, when you take a look at this, because of the skew, the time taken for these two jobs, let's go to the queries, okay? So because of the skew, because of that massive skew on one task, the time taken for this query is 3 seconds. Whereas when after we salted that skew, the time taken is 0.4 seconds. You see how big of a difference that salting made, and that is how it works. Salting just, makes it easier for it. Yeah, basically the flow is same, but salting makes the process easier. And because of that, the duration taken is relatively very low for that. That's how we can deal with skews. And yeah, with that, we are done with this topic, and let's move on to the next one. Now, our next phase will be user-defined functions, and our next topic will be what user-defined functions actually do internally. Yeah, in PySpark, we can actually define a function, but we can define the function in Python and not Spark. And there are equal trade-offs of using it. We don't have to use UDF. We'll not get a situation where we have to use UDF typically, but if you have to, if you want to, or if you have to remember these things. You can only define a function in Python and call it as UDF into PySpark and run that function. But when you do that, it has to be executed outside the JVM. You know that, right? Spark basically runs everything in JVM, Java Virtual Machine. But when you want to run a Python user-defined function, it has to be run outside PySpark. And this is how it is done. Okay, so when you call a user-defined function that you defined, what happens is it serializes the data, right? It serializes the data and sends that data from JVM, Java Virtual Machine, to Python objects, converted to Python objects, and then that will be executed. The user-defined function will be executed. But here's the thing, because the data is out of the JVM and it is run using Python, there will not be distributed batch processing. You have to go row by row execution, batch processing, just a normal batch processing on a single machine. There will not be distributed processing. No matter what the user-defined function has, it has to be executed row by row in a normal batch processing and not distributed. And result of that will be loss of optimizations, because that makes the system a lot slower, because that runs on a Python machine, Python environment. So Catalyst cannot see inside UDF. We know what Catalyst is, right? Catalyst is present in Spark that converts the logical plan to physical plan, which optimizes the logical plan basically, and we don't have access to that when we execute a user-defined function in Python. Now I'm going to show you an example how we can define a function and call that user-defined function. Okay, here I'm just going to copy paste again. I'm just creating a data frame with one column, which is value and has 1 million records. And importing call. Now I'm going to run a built-in function to transform the data, which is nothing but doubling the column, which is value, doubling the value column by multiplying it with 2. Okay, now I'm gonna run an action to execute that plan. 3, 4. So that added 1 job. Okay, and it took 0.2 seconds to execute. Now close that. Now I'm going to import UDF, user defined function. We need that module to run a user defined function in Python. Import integer type. Now I'm defining the Python function def double of x return x times 2. This is the function, and that's the end of the function. And double UDF, we're calling that function from Spark here with this line. Double UDF equals UDF of double value, double underscore value, integer type. So we're calling double value function. We're saying UDF, we have to say UDF of, and the function name, which is double value, which we defined before, double value, and the output should be integer type. I run that, and I create a new data frame using call again, but here I'm going to use the user defined function UDF, name it df underscore UDF equals df dot with column, and name the column as double underscore value double UDF, double underscore UDF. So I'm calling this variable of call of value run it. And here's the thing you have to take a look at. When I used PySpark built-in function with column and say column of value times 2, we are running that, we are multiplying each row or each field in that column with 2. Yes, so it goes, the expression is applied to every row. That's fine. But when what we're doing here is we defined a Python function, and we assigned it to this variable, and we called that function and passed call of value. Now what happens is every single value, every single field in that value column will be given to that function when we call the function using double UDF, given to that function one value at a time, and it goes it serializes that, and it goes out of JVM and it goes to Python environment, and then it runs this function and multiplies that with 2 and returns that the data back by deserializing, and it gets back to JVM from Python environment, and then gives the output for one particular record at a time. And that has to be repeated for every single one of that field, which takes a lot of time. And that is why user-defined functions are dangerous to use unless you have no other alternative in Spark. Whereas here, we do have alternative to multiply too. So we don't need it, but I'm just going to explain how this process is going to work. I'm going to run UDF df underscore UDF dot show off. Run it. Now we get the same output, right? We get the same output. Output doesn't change. Now let's go here, go to this, refresh. Okay, now this is the execution we done with the built-in function in PySpark to multiply with 2, and it took 0.2 seconds. Whereas the program, the application where we used user-defined function, which is this one, this action took 0.5 seconds to execute. It is more than double the time that it took with the built-in function in Spark. That is why we have to be careful when we use UDFs. And yes, with that, we're done with this topic. Let's head to the next one. And for our next topic, we have when UDF are justified. Like I said, we only have to use UDFs when there is no built-in functions in Spark. And there are multiple other ways too. If there are no built-in functions, built-in Spark functions, no Spark SQL expressions. You can also check Spark SQL expressions. Even if you don't find that a way to execute that, and if it is a higher order function, an SQL case when logic, which you cannot execute in this environment, only then we can rely on UDF. So you have to treat UDF as your last option and not a design tool. Now, before going to UDF, you have to check in with the built-in functions like when, case, reg, exp, map, array, and you also have to check in with higher-order functions like transform, filter, exist, and SQL expressions can be written using expr off, and the join-based enrichment window functions. Check everything that Spark has, and even after checking everything, if you didn't find a way to execute that, only then you have to go with the UDF functions. I mean, user-defined functions, which will be run in Python environment. And yeah, this topic is nothing but talking about when to use UDFs and when not to. With that, we're done with this topic as well. Let's head to the next one. And in this phase, we are going to talk about data writing and storage layer. And our first topic will be Spark Data Writer API. Unlike the other tools, we cannot just write the files directly because this is a distributed system. You have to understand how we write the data. So we use Data Writer API basically to define how data frames and data sets are materialized to storage, basically to be stored in a file format outside in an external storage. So we have to know about the data writer API. We already know about data reader API. Now we are going to talk about data writer API. And so this is a basic format, basic syntax. We say, just like the read, we say df dot write dot, and we define the format, and we define the path where the destination path. Whereas in read, we use load off. Here we use save off to define the destination path. Whereas in read, we define the location of that file. Here we define the destination path using dot save off. And we also use something called mode, and it is optional. If we haven't defined anything about the mode, it just by default takes append as the mode. We'll talk about the modes later, but for now, we're going to talk about the writer API, and this is the basic format. Now let's head to the commit protocol. What happens here is, because the data is distributed into partitions, when we write the data, all the tasks that has all these partitions write the data into temporary files, temporary files that are stored in temporary locations because of that. And then driver validates if the tasks are successful, and if they are, these files will be moved to the final destination. And that is the reason why before previously when we write a file, we had multiple CSV files or multiple files created for one data set because of that partitioning of data. And we also talked about combining that later, right? Yeah, we'll talk about it. Okay, now let's head to the lab. I'm going to create the sample data first. From that, so this a simple list of tuples which ranges from 1 to 100, which means it has 99 records. And I used f strings here for for the second value in every tuple. Now I'm going to convert this into a data frame, a Spark data frame, before I write that into a file, an external storage. On it, that will create the data frame. Run it. Okay. Here, first I defined a variable with just the output path just to separate that. And then I wrote that data into that particular path using df.write.mode as overwrite. We will talk about the writing modes, but now I'm going to use overwrite dot. This is a file format. We already talked about it. We can separately say dot format of Parquet and dot save of and the output path, or we can combine them together and say dot Parquet of output path. Both does the same thing. It's just about the readability, and it is easier to write this rather than that. Now this will create What is that? Spark writer demo. The Parquet files in that location. And because the system is distributed, the data is distributed among the partitions, the output files will be multiple, like that. Because the data is partitioned into 4 partitions, the output will also be having 4 Parquet files, and each of them have their own data basically, and they are each of these Parquet files, or whatever the file format that is, it doesn't matter if it is Parquet or CSV or JSON. If we write that file using Spark, it creates these files in the same folder, which are .crc files. What these does is it captures that particular file's inputs and outputs. Okay, I mean basically the data movement in that file. And for every file there is a dedicated CRC file. For this Parquet file there is this dedicated CRC file which captures every data change in that particular file. So if any external source changes that Parquet file, Spark will immediately know the data is corrupted. That is how CRC files work. They check when we read this file again, Parquet goes through these CRC files and compare these CRC files with the actual data file, the Parquet or CSV file, and sees the flaws in that and compares the flaws, and if there are any flaws, Spark will immediately know there is some sort of corruption happen in the data. That is how these CRC files work. And this success file is created because the process is successful, the writing process is successful. There's nothing to do with that. And that success file also has CRC. Yes, that is how CRC files work. I think you got it. Now, yeah, that's it with this topic. Let's head to the next one. Now, our next topic is 8.2, writing modes. When we write a file, there are multiple writing modes. There are 4 writing modes in Spark, and depending on our situation or the scenario that we want to implement, we chose one of these modes. And by default, it is set to error mode. If you never defined any mode, it is set to error mode. I thought it is set to append, but no, it is set to error mode. I have to correct that. And each mode have its own way of execution of that write. So firstly, let's talk about append mode. When we write the data, we write the data in this way. We say df.writeOf dot mode of append. What append does is it doesn't care about whatever the data that is already exist in that file, in that location that we are going to write, and just adds. Appends means it just it just adds or combines the new data to the end of the other data. It will not care about the data that is already present. So that is what it says. The behavior adds new files, never deletes the existing data, does not check for duplicates. Okay, that is what append is. Whereas overwrite mode, we write it in the same way. We just say overwrite. What it does is it doesn't care about the data. It don't read the data. If there is any data already exists in that location where we are writing, it just replaces, it just overwrites the data with this new data, no matter what data it is. It doesn't care if it is duplicate or if it's not, if it is a new variant. It doesn't care. It just overwrites the data with the new one. And there is the other mode, error, where fails, where the execution, the write fails if the data is already exist. So there is error mode, which is the default mode. It fails if the data, if a duplicate of that data we're writing is already exist in that particular location. And there is ignore, which ignores that data. which ignores the errors silently without triggering an error. Unlike the error mode, if we say error mode, if the data is already present in the duplicate data is already present in the destination, that will trigger an error. Whereas ignore mode, it doesn't care about that. It just skips the write completely. That is one of the mode. So we can use all this mode according to our preference, and they have their own properties. So if we use append, there is a chance of us getting duplicate data because it doesn't care about the data that is already present in that location, right? So there is a chance of us getting duplicate data. Whereas overwrite, because it just overwrites all the files, it just deletes the old files and replaces them with a new one. There is a chance of data loss when we use overwrite. And if we use ignore, there is a chance of silent failure because it just ignores the failure and it will not trigger an error and it moves on. So these are the downsides of each of those modes. And there is one more mode I have to talk about, which is override plus partition. This is the most used mode. Not the most used, advanced and the real world capable mode, which we say dot mode of override, and then we say dot partition by date, which what basically this thing does is, it depends on the settings, by the way. So we also have to run this to change the setting where spark.sql.sources of partition over write mode should be dynamic. By default, this will be set to static, but we have to convert this into dynamic. And when we convert that to dynamic, it checks for the data, and if it finds any duplicates in the data, it only replaces it only skips the, not the duplicates, by the way. If it When it read the data, if it finds the same data that we are writing already exists in that data, it skips that data, but it only adds the new data to that particular destination. That is how this works. So now it doesn't cause any data loss and it doesn't cause any duplicates too. So that is the most real world advanced mode to use. So now let's head to the lab for this. I'm going to open the command prompt. For this, I'm going to create a small data set, very small data frame. Say A. Run it and convert that into a Spark data frame, obviously. Now first, I'm going to use the overwrite mode. Okay, and this, what's that? Name path is not defined. Oh, this should be the actual path, which is /opt/spark data slash write mode demo. This should do. And now I forgot to close the quotes, double quotes. Have to close them, run it. Now this will write the file in that location, which is write mode demo, and we can actually see the Parquet files here. And that created 3 Parquet files, okay? Now, I don't need to demonstrate overwrite again because we know overwrite doesn't care about anything. It just replaces the data file with its new data. But what append does is, even if it has duplicates, it just adds some more files to the same location, right? So we're going to do that. Run that. Again, I just forgot to write the path. I'm going to copy paste that and replace it with append. That should do. Now run that. What happens is you'll see the same 3 files added again. See that? Part 0, and the same file. If you open that, I mean, you cannot open them here in the notepad, but if you read those files back again, you can see the duplicates that are in those files. You know what? Let me just read it and print them to see the duplicates, basically. So let me do that. Say df read equals df dot wait df underscore read dot read dot say Parquet so there are 2 dots. All right, so Parquet doesn't need format. We don't need to define the format for Parquet, so we can just read it like that. What happened? Okay, well, I think I forgot the syntax of it. Okay, let me try that again. Now copy that. Should be equals Spark then dot read dot Parquet. This should work. There you go. Now df read dot show off. See that? So the duplicates are not taken away. They are just, the new data is just appended to the old data. So that causes duplicates. Now let's try that with the other options available. So before doing that, I'm going to run this override again, just so it removes the duplicates. Let me check that. So it removed the duplicates. Now the next mode is the default one, which is error. For that, I'm just going to copy paste this and remove the mode totally, because that is the default mode. When I run this should trigger an error saying the path already exists. So it says the data is already exist, and that's why it popped that error. So this is how the mode error works. And we're now going to use the other mode, which is ignore. It ignores. It doesn't care. If the data is still there, if the data has duplicates, it doesn't care, just skips the process. That's how it works. Okay. So it still run that job, but it still run the query. It never created a job because it doesn't care. It just skipped the execution because the data is already exist. And that's how ignore works. Now, I think I demonstrated all the 4 modes. With that, we're done with this topic as well. Let's head to the next one. We're almost done with the masterclass and we are at phase 9, which is tables, metastore, and Spark SQL. And our first topic is manage tables and external tables. Spark tables are nothing but they act like SQL tables, but in Spark environment. They are stored in metastore with logically in metastore with the schema and the location metadata along with it. So they work, I mean, almost like an SQL table. We can run SQL queries on it too. So they are like abstraction of the data files. And there are 2 types of these tables. There is managed table and there is external table. The major difference between these 2 tables is the managed table is controlled by Spark. It doesn't actually, it does actually store the data in the table. So if we drop the table using drop table SQL query, if we drop that managed table, the data will be gone with that table. Whereas on the other hand, external tables are the tables that only stores the logic in metastore but they are virtually connected to the external source. So if the external source data is deleted, this external table will be deleted too. I cannot retrieve the data from that source. But if we drop this external table, nothing happens to that external the data that is stored in that external location. That is how these tables work. Okay, let's see what theoretically they are called. So the managed table means Spark controls the table metadata, obviously. Spark controls the data location, yes. Dropping the table deletes the data. Like I said, if we drop that managed table, it deletes the data. The data goes along with it. On the other hand, we have external table. Spark manages the metadata only. Data lives at user defined location and not in Spark defined location. It lives in external user defined location, not inside the metastore. Dropping the table does not delete the data. But if we delete the data in the data source, the table becomes unusable because it is connected to the data source and we deleted the data source. That's how these 2 tables work. Now let's put that into practice and see what we can do with them. I'm going to open the PowerShell and I'm going to create a simple data set, data frame, and then convert that into, save that as a managed table. And then after that, I'm going to save that as, what is the other table? External table. Okay, let's see the difference here. I created that basic list of tuples again and df equals Spark and I create the data frame out of that data, the list of tuples. And now I'm going to write the data as a managed table into the metastore. I'm going to use the write mode as override because, well, we don't have any data anyway, but still I'm going to use that. Save as table of managed demo. Run that. So we haven't got any errors, but we got multiple warnings. I'm just going to ignore them for now. So let's see if that is actually created by using Spark SQL and run an SQL query in the metastore. Say select all from managed demo, quotes close. Then I'm going to run the action to show the result of that query using .show off. Run it. Okay, I guess that's why I got the warnings. Maybe we don't have a metastore configured because we are running on my personal PC and we don't have any metastore configured. We have to configure that. But for now, that is how it works. For this is just fine for the demonstration. You can actually see the table, the abstract of the table that is created, but the data is not saved because we haven't configured the Hive metastore. But if you run the same commands in Databricks, where it does have Hive metastore, you can actually see the values and the data saved in it. Now I'm going to leave it aside and show you the external table. That will work because that doesn't store the data in the metastore because that points to the external source and not store the data. Use df.write again and mode. I'm going to say overwrite dot option of path. When we define an external table, we have to define the path in the options and say option opt slash spark hyphen data slash external demo dot save as table external underscore demo. I run this thing. That creates the external table. Now, if I query from that table using the same spark.sql, select all from external demo, and show to trigger the action to show the output of that query. Run that. That will print the data, right? And if we go to that destination, the location where we pointed the destination to, we can actually see the file written here, which is external demo. Is right here. Yeah, all the data is here, and the table is just pointing towards that location, that file. If I delete this file totally, say delete that. Now if I run this query again, error, because the external data source is deleted, but still it does have the external table abstraction, but the source is deleted, and that's why we got the error. Oh, that's a big error. See? So it searched for that files that it is pointed towards to, which are Parquet, Parquet 1, these files. So it says it doesn't exist because it is deleted. That is how external tables work. And with that, we're done with this topic. Let's head to the next one. In this topic, we're going to talk about Spark SQL Execution model. I already gave you guys a glimpse of how we can run SQL queries in PySpark in the last example where we used spark.sql off and quotes and we wrote the query there. We can actually use Spark in that way. We can write queries. And it is not even executed by a separate execution engine. It is still executed by Spark, but it is just declarative, and PySpark is programmatic. So if you are comfortable, let's say when we work in an environment, and if a person, let's say if someone who is only familiar with SQL and not much familiar with PySpark, he can use SQL in PySpark, so he can get that distributed computation power, just like PySpark. That is what PySpark offers through spark.sql off. So we can run queries and they execute exactly as Spark programmatic code. So they are still compiled. The SQL queries are compiled, and the same thing happens. The logical plan is created, and the catalyst optimizer optimizes the logical plan and converts to physical plan, and everything is same. Everything is same. The only thing is that is declarative and this is programmatic. That's it. Now, see that? So we write, if you write a filter in PySpark like this in the data frame API, basically the data frame API is what we used until now in PySpark. So using data frame API, it looks like this. We filter out a column named amount to only have, filter out the rows by the column amount to only have amount greater than 1000, and we write the same thing in SQL the same way. Select all from the table where amount is greater than 100, the same filter but in a declarative language format, and nothing changes. So let's head to the next let's head to the lab and to see if anything changes between the declarative and the programmatic approach for a transformation. I'm going to open the PowerShell again, back, and create a data frame. supposed to be comma. We created the Python list, and now we create a data frame out of that. Run that. That will create the data frame. Now, if I run df in the df data frame format, so I'm going to say df underscore df dot filter of df underscore amount greater than 1000. Okay. Copy paste it. So it's not df underscore amount. It is just amount. So we can say df dot amount. That works too, by the way. You can say df dot amount or just amount. That works too. Say 0 greater than 1000. Run that. Now df underscore df dot explain of true. Run that. Now this will print the physical plan, the logical plan and the physical plan. And here's the physical plan. Here's the logical plan. Filter, logical, RDD, and stuff like that. Now I'm going to execute the same thing with Spark, with SQL, and see the difference. df underscore SQL. Thousand. So if you are good at SQL and if you're comfortable with SQL and you want to use it, you can use it in PySpark as well. Now I'm going to run that. There is an error, and the error is oh, there's nothing wrong with the expression. What is wrong is I forgot to write an expression for that step. I forgot a step in between where we create a view from the data frame, because we cannot execute an actual SQL query directly onto a data frame. What we can do is we can create a view out of that data frame and then execute SQL queries on that data. On that view. So we have to create a view. To create a view, we say df dot create or replace and create a temporary view of, and say, and call that view as sales. Run that. Now the temporary view is created. Now I'm going to run this query. That will be executed. And then we run df underscore SQL dot explain of true. And there we can get the logical and the physical plan. If we compare these two plans between the actual data frame transformation and the SQL transformation, the DDL transformation, the SQL transformation, not DDL, what we can see is the fiscal plan is exactly the same. You see that? So the first step starts with a scan existing RDD, and the second step is filter the amount out of it. And the same thing happens here as well. Now, where is the fiscal plan? There you go. This is a fiscal plan of data frame API. Scan existing RDD and filter that out. 2 steps, simple, right? And we can get output for both of them. Let me just run an action to get the output. Run that. We get the output for this one, and also for this one. We got it. We got the same outputs for both the processes, and let's refresh this. This creates 2 queries and with 2 jobs. This is a fiscal plan. Scan existing RDD, filter, project, collect, limit. Same thing. Scan existing RDD, filter, project, collect, limit. The fiscal plan is exactly the same, but the logical plan is different because we're writing that in SQL. But by the end, the fiscal plan is same for both the ways. Okay, with that, we're done with that topic as well. Let's head to the next one. Now, our last phase and last topic of the masterclass, which is Spark streaming. Most of the people think streaming processing in Spark is a lot different than batch processing, but no, not. I mean, most of the part, the transformations and everything are exactly the same in both the cases. Only the thing that changes is the input and output will change. Instead of us writing spark.read whatever the file format, when we read the data from a read the data in batch processing, in stream processing we use spark.readstream.parquet. This is how we do it. And the same way, when we write the data, we use spark.write in batch processing, and in streaming we say spark.write stream in streaming processing. And there are other few things, few minute changes in the transformations too, but most of it is same in streaming and batch processing. So don't get confused. And I am going to come back with a project, and I'll release that within a week from now, which I'm going to show you. I'm going to execute in which I'm going to do a small project on PySpark, which is basically focused mainly on PySpark, and I will upload it within a week. So you can just, sharpen your skills after this masterclass. So yeah, if you see this video after a week, I might already upload the video. If I upload the video, I will remember to add that in the end screen and also in the description, so you can just check that out. With that being said, this is the end of the masterclass. I will meet you again in the next video. Until then, adios.